So welcome to day 2 of the marathon course on the Bayesian story. I have some new items to orient you to. The web page, the page I'm going to be maintaining from now on has changed its name slightly. When I first started building it, eBay was the only sponsor, but now it's jointly sponsored by eBay and Google. And so if you go to the old address, which is just the same thing without the Google, you'll get a page that says, don't come here anymore because the web page is moved and there's a click to get to the real web page. So from now on, this is our new web page. I'm sure there's a more elegant way to do that, but at least it works. Thanks to Jeffrey Oldham, I have put information, including maps and building numbers, for all of the sessions from now on. So I hope that'll be helpful in finding your way here, those of you who are not Googlers. And then at the bottom, we have some new content. First of all, under supplementary reading, I wanted to mention to you this wonderful book by this guy, Ed Janes. As I put it on the web page here, it's the single finest book on probability and statistics I've ever read, and I have read it multiple times, and I continue to read it and get useful stuff out of it. So see if I can show you what it looks like on the document camera. So it's from Cambridge University Press, and it was published posthumously. It was put together by his student, Larry Bretthorst, who's the editor of the volume. And so certain sections of it toward the end of the book just sort of taper off and into silence when he would have definitely done other stuff. But the stuff that's in the book is extraordinary, and I recommend it to you highly. So from last time, the 11th of January, we covered all those lecture notes, and I have posted, I went through most of the handwritten notes from last time, but I've also posted the extra notes. Each day there'll be a block of handwritten notes that I've prepared beforehand, and then a block of new handwritten notes just on the spur of the moment here. And so I posted them since last time as well. Oops. And we have a whole bunch of new stuff this time here. We began Lecture Notes Part 2 last time, and we're going to continue that today. I'll talk a little bit about this handout on using Bayes' theorem to help build a spam filter. Oh, I'm on the wrong. Thank you. Please help me with that whenever I do that, because obviously I'm having a conversation with myself at times like that. So there's a handout that has not been updated recently, but has some interesting material in it about how to use Bayes' theorem to construct spam filters, and I'll talk briefly about that today. Some years ago, I was working on a book on Bayesian hierarchical modeling, and then I got sidelined writing papers and other books. But the draft is available here, and you'll find the beginning of it to be quite readable as a summary of much of what we've been doing last time and this time. And then later chapters cover simulation-based computation, which is going to be one of our topics that we'll get to after we do the things we're working on now. There's now a new problem set for you and solutions to them. And we're going to be working more and more with a variety of probability distributions. So one of the books I recommended to you to consider reading out of if you had extra time was this book by Gelman and Carlin and Rubin et al. Called Bayesian Data Analysis, second edition. Gelman, Carlin, Stern, and Rubin. And there's an appendix in the back called Standard Probability Distributions, in which they cover, just like it says, most of the standard probability distributions. You have information about the notation that's used and the nature of the parameters, the density function, and then some basic summaries like the mean and the variance and the mode of each distribution. So a very handy small table with all those things in it. And I photocopied that for you and put it here. And for some reason, it looks like I had to do the photocopying sideways to get everything to fit. So when you print it out yourself, it will be easier to read than it is on the screen here. And probably there's some way to rotate it also, but no need to go there now. Then there's what's that? Oh, thank you. We're going to have to do a lot of that possibly today. I didn't get much sleep last night. So this is a wonderful article by these guys, Kahneman and Tversky. They are, Tversky is unfortunately dead now, but Kahneman is still very much alive, and not long ago won the Nobel Prize in Economics for their joint work. And the judges said that if Tversky had been alive, of course, it would have been a joint prize. They are basically psychologists who have spent their lifetimes summarizing the ways in which we as human beings are not innately correctly wired to process uncertainty, And an example that connects with one of our examples last week, right here on the first page, I can talk you through it. Suppose we make a list of all of the practicing librarians in America, and we make a list also of all the practicing lawyers in America, and we merge those two lists together, and I pick one person at random from that merged list. And now I'm going to give you some information about this person. Turns out to be a male, and the information is in this middle column. Steve is very shy and withdrawn, invariably helpful, but with little interest in people or in the world of reality. A meek and tidy soul, he has a need for order and structure and a passion for detail. And I ask you on the basis of that data and the nature of the sampling, whether you would put bigger odds on that person being a lawyer or being a librarian. And you can tell where this is going. The data, what we called last week the Bayes factor, when we write Bayes' theorem in odds form, the Bayes factor in favor of librarians sounds quite strong here because all of those things were better suited to a librarian than a lawyer. And yet, we know from Bayes' theorem that that's not the only story. We have to multiply the data odds through the Bayes factor by the prior odds, and there are an enormously larger number of lawyers in the country than there are librarians. And so the right answer is that even with that information there, it's still much more likely that the guy's a lawyer than that he's a librarian. And almost everybody gets that wrong when you don't take them through a course in careful logic involving Bayes' theorem. Almost everyone gets it wrong, and they have many other examples of standard biases that many of us, well, most of us, I guess all of us are sort of born with, and then we have to work in our lives to try to fight against them. Another one that you will find interesting probably is something they refer to as availability bias. We all remember with great vividness all those times when we were in an enormous hurry to get somewhere, and the traffic lights all went against us. And so you have a feeling that you're one of these people who just hits a lot of traffic lights just at the wrong moment in your life because there it is happening to you all the time. But in fact, what's happening is that you remember and can recover those incidents in which the light stopped you far more readily than you remember all those times when the light didn't stop you. And so you end up having a built-in bias to think that rare things are actually more frequent than they are when those rare things disadvantage you, for example. So there's many things like that in this article, and I very much recommend it to your attention. It'll be excellent supplementary reading in parallel with what we're doing in here. And then there's an article from the New York Times, which I'll talk about at the appropriate moment in the lecture notes. There's an economist who writes a lot for the New York Times named David Leonhardt, and I recommend his copy to you. If you like to read the New York Times, you can look for his name because he's a very thoughtful person, and he sometimes writes about Bayes. He almost always writes about something quantitative. Typically, it will have an economic focus, but not always. And the guy's invariably thoughtful, and this is a piece about a situation where scientists in England were prepared to use strong information external to the present data set, and in so doing got a much better answer than the parallel analysis that was published in one of the leading medical journals in England, which was based on instead on only the data evidence from the one study that was conducted. So I'll come to that at the right moment in the narrative. And then we have today's handwritten notes, which I'll brief on the document camera to you as they arise, and a placeholder for the extra notes that will come from today's class. And then if we get there today, there's a part 2 of the lecture notes, and then also a part 2B. Today we're going to finish talking about discrete outcomes, binary outcomes in the case study involving the heart attack mortality example from the Dominican hospital that we began last time. And time permitting today, or else we'll do it next time, we will move over to integer valued outcomes and talk about Poisson modeling from the Bayesian point of view, working our way up after that to modeling continuous outcomes with Gaussian and other distributions, and then seeing how that story unfolds. And there's a new section at the bottom of the web page which begins to give us some code for the first time. So I'll be giving you R code, sometimes on the web page here, sometimes embedded in the PDFs. And it's very easy just to go ahead and drag with your mouse and grab the code that way out of the PDF. But sometimes I bring it right here. And the code here will always be either in R or in WinBugs, which is going to be our engine for Markov chain Monte Carlo in a few weeks. There will also be data sets as we go along as well. So far, the data sets are small and not necessary to post here to actually work with. So that's where we were before. Before I go any farther, does anybody have any questions or comments, having perhaps spent some time on anything in problem set 1 that they would like to bring up now? And I don't mean by asking that question to I'm not trying to elicit guilty looks on your face if you didn't actually get around to looking at the homework. The homework was meant to be supplemental and for your benefit if you had time. There's a new homework set this time. I'm going to try to have a new homework set every single time for all 10 weeks, but I may fail toward the end of the class, so the frequency might not be quite that large toward the end. The first problem, just to orient you to it, to see whether you do want to work on it if you haven't yet already, the first problem is an extension of our case study about updating in light of the ELISA results to see whether that guy was HIV positive or not. And it goes in much more detail into the nature of medical screening tests. So we had the ideas of sensitivity and specificity and prevalence were the things that drove our case study last time. The people who think about these things are also interested in quantities called positive predictive value and negative predictive value and other quantities like that. And so this is an opportunity for you to explore these ideas in greater detail. Then there's a problem on Mr. De Finetti's approach to trying to create logical internal consistency. I believe we talked last time about the concept called coherence. Did we speak about that last time? The idea there was De Finetti's definition of probability, as you may recall, was based entirely on the concept of betting odds. For you to figure out what your Bayesian probability of something is, based upon your current information base and also your own particular background information and assumptions and judgments, you have to query yourself. You're thinking about a true-false proposition whose true status is unknown to you at present, and you have to query yourself about what betting odds you would be comfortable either giving or receiving in order that you judge the bet to be fair. So you move the betting odds around in your mind until you get a point where you would be happy to take either side of the bet, and that's the point at which you convert that odds number into a probability. So that was Mr. De Finetti's way of thinking about probabilities. It's related to Mr. Bayes' way, which was based on expectation, also in the context of betting. And De Finetti invented this idea of coherence, and coherence was a way of seeing whether or not two or more of your probability assessments that are offered to someone else simultaneously are logically internally consistent. So if your world of probability is based on betting, one of the most direct ways that you could show someone that there's something wrong with their probability assessments is to show them that if they listen to your betting odds and your probabilities, you're able to offer them a series of bets which has the property that no matter what happens in the world, you lose money. And that's called making a Dutch book against you. And so this is a problem that shows you actually how to do it. I'm interested in professional golf, and this is some data from a golf tournament some years ago. There was a guy on a webpage called sportsline.com called Mark Scholtau, and he published an article about the Masters golf tournament, one of the big major tournaments back in 2001. And here's a table of all of the odds against the players winning. And what you discover when you look at the table is that it's incoherent, because if you convert all these probabilities, these odds to probabilities, and add them up, they don't add up to 1. So if these were Mr. Scholtau's actual probabilities as determined by his odds, then it would be possible to make Dutch book against him. And the problem explores how to do that. So if you have an interest in that sort of thing, that's a problem in which you can explore that. Then there's the famous old Monty Hall problem that probably everybody's heard of before, with the game show in which there's 3 doors, and behind one door is a valuable prize like a car, and behind the other 2 doors are less valuable prizes like a goat. And the problem assumes that you would like to find the car. You pick a door, possibly at random, and Monty Hall knows where the car is, and his job next is to choose one of the other doors and open it and show you that there's a goat there. So that he gives you data that the car is not behind the door he opened. And that leaves one door unopened at the moment. Actually, 2 doors that are unopened, but one door that's not mentioned so far. You picked one initially, and then Monty Hall showed you there was a goat behind the second door. So the question is, should you stick with your original door or should you switch? And it's quite straightforward to use Bayes' theorem to discover the nature of the information Monty Hall actually gave you in showing you that that particular one door did not have a car behind it. So I've suggested to you how to set the problem up to use Bayes' theorem to work out what the right answer is, and also to figure out how to explain in non-technical language what the result actually is. And then there's some problems that there's a problem that you can go through to practice on doing basic calculations with the Gaussian or normal distribution, having to do with point spreads in betting about football games that you might find interesting. And problem 5 is one I wanted to especially talk with you about because it has an important implication for the Bayesian paradigm. So we have a proposition A whose truth status is unknown to us, and we gather some data D, and it's also in the form of a proposition. So this is just like the Eliza case study last time, where A was whether the guy was HIV positive or not, and D was whether Eliza came out positive or not. And so it turns out that no matter what the data set is, how the data comes out, as long as it's in such a way that the probability of the data coming out that way is a positive number, and not equal to 1 either, so it's strictly between 0 and 1, then if you force into Bayes' theorem the prior probability of the truth of this to be 0, then it turns out that the posterior probability of A, given any data, is still 0, no matter what. And moreover, if the prior probability of A is 1, then the posterior probability of A, given any data whatsoever, is also 1. So in other words, there's something strange that happens with Bayes' theorem at the extremes. If you put in prior probability 0 or prior probability 1, from the point of view of a learning model, we're in serious trouble here because no matter how the data comes out, your posterior probability is the same as your prior probability. And that's a terrible way to set up a system to learn from the world because you want to be able to change your prior information based upon the data information. So this is called Cromwell's rule. The name was invented by a great British statistician, Bayesian, named Dennis Lindley, who's not too active now, in his early 90s, but still alive. And he called it Cromwell's rule because he was a student of English history, and he was speaking about Oliver Cromwell. There were several Cromwells in English history, and Oliver Cromwell was not a very good one, actually. But in an exchange of letters with the elders of the Scottish Church, Oliver Cromwell once said to them, I beseech you, in the bowels of Christ, think it possible you may be wrong. And basically what he was trying to say, according to Mr. Lindley, is, and I don't mean to be too geekish about this, but basically if you take that sentence and try to translate it into information processing, he's basically saying, be prepared to change your mind based upon new information. And so this rule is an example of a situation where even if you were prepared to change your mind based on new information, you can't, because you have such a dogmatic prior that there's no room for any learning. And so what this tells us as Bayesians is that we should try really hard never to put prior probability 0 on anything that we think might actually be true, any proposition that we might actually think might be true. Because if that's so, and we don't have an opportunity to go back and change that prior probability, we will never have an opportunity to learn otherwise. The world can never show us we were wrong. And similarly, try really hard never to put prior probability 1 on anything unless you are absolutely certain that it's true, and you never want to back down from that assertion. Because again, having put prior probability 1 on something, formally, without having any mechanism to go back and change your prior probabilities based on something that really surprises you in the world, there's no room for you to learn. And that in itself brings up an important question. Is there room in the Bayesian paradigm for people to notice that their prior specification was wrong and go back and change it without the something for nothing bell in all of our heads ringing? Because if you look at the data and it shows you that something about your prior is not what you would like to have, you would like as a scientist to be able to go back and change your prior based on what you saw in the data. But you remember the role of the prior is to bring in information external to the data set, and the role of the sampling distribution is to bring in information internal to the data set. And if you use the data set to see that the prior was wrong and you go back and change it, then you've used the data twice. And the result will typically be uncertainty assessments that if we're trying to construct intervals, we think that the truth is somewhere between 3 and 5, let's say. Would you expect in the situation that your intervals would be narrower than they should be or wider than they should be or about right? Whenever I use the data twice and then go on to build a model which yields intervals, uncertainty intervals about something that lives on the number line, for example, do you expect, by having used the data twice, do you expect those intervals to be about right in how wide they should be, meaning reasonably well calibrated, or rather systematically too narrow or rather systematically too wide? What would be your intuition? And some people are saying too narrow, and that's got to be right? Because if you use the data twice, it's a kind of form of cheating. It's as though you're pretending you have more information than you do. That's going to make your intervals narrower than they should be, and the result will be you'll find that you're not in good calibration, and it will be in exactly the worst direction. Your intervals will not include the truth as often as you hope they do, or as often as you announce that they do, and that is, of course, the worst direction to be miscalibrated in. If I go around quoting so-called 95% intervals all my life, and in fact 98 or 99% of them include the truth, that's not great, because I was going around giving people wider uncertainty bands than they needed to, and that forced them to hedge a little bit extra against uncertainty unnecessarily. So that's one kind of mistake, but it's not so bad. But if I go around quoting people so-called 95% intervals all my life, and actually they include the truth 65% of the time, that's really bad, because people are counting on me to give them an answer that's right 95% of the time, and I'm letting them down with a piece of machinery that's only getting the right answer 65% of the time. So my intervals are going around being rather sharply narrower than they should be, and the result is that these people that I'm working with have not hedged enough against the real uncertainty that was present. So we always want to try hard not to use the data twice, because that will lead to miscalibration in the direction of pretending that we know more than we do, and the result will be intervals that are narrower than they should be. And yet, we're going to see by the end of the course that it's vital for all statisticians, whether they be frequentists or Bayesians, to be able to not only model the data, but to go back and remodel the data based upon surprises. And so there has to be some kind of Bayesian story that allows you to go back and change things in the Bayes machinery. And I won't talk about that until much later, but I and other people have figured out a way to do that that has a decent chance of helping you still arrive at good calibration. Essentially, it's a form of cross-validation, which is something probably everybody in the room does all the time when you're analyzing data. The standard thing to do is to partition your data into 2 non-overlapping and exhaustive subsets and do modeling in one part and see how well it validates in the other part. But what happens if, in fact, you discover, having done that, that the modeling does not validate very well in the validation subset? Then you have a powerful desire as a scientist to go back and remodel and revalidate. And in fact, that's what we do all the time. There's a kind of iterative cycle of model, validate, remodel, revalidate, and keep doing that until we finally got a model structure that validates well. But now you've discovered that you painted yourself into a corner. You don't have any new data left over that was untouched by the modeling process to find out how well calibrated that entire iterative process is on future data, which is can be proxied for. Now, why is this happening, I suppose? It seems to fade in and out. You want to use some data somehow that hasn't been touched by the modeling process. And so in a simple extension of the usual 2-way cross-validation idea, I and other people who like this idea would put forward a notion involving 3-way cross-validation. And the idea is to partition your data into 3 non-overlapping and mutually exhaustive subsets. And the picture goes basically like this. I'm going to go over to this thing and see if probably still have that problem with the pinkness. I'm not sure. So if you take your data set and partition it into a modeling part and a validation part and a calibration part, then you're allowed to model and validate and remodel and revalidate all you want. But when you're done with all that whole process, you have a nice pristine block of data down here to report two kinds of answers to people. Answer number one, the actual inferential or predictive or decision-making answer to the problem you started with, and answer number two, how well calibrated the machinery is that led you to that answer in part one. And so this is called, I call it calibration cross-validation, CCV for short, and we'll be talking about that at some length later on. So there is a Bayesian way to cheat by looking at the data to figure out what good models are, which is what we all do all the time anyway, but pay the right price for it. And the price shows up in the size of this calibration data set here, because if you're using this data not to do the modeling, then the actual effective size of the data set is smaller for the modeling purpose, and your intervals get wider. And if you use Bayesian decision theory to figure out how much data to put in each of these parts, the intervals become appropriately wider based upon how you trade off those two goals against each other. So there is a story here. Shall we try back again on the other guy and see if we're still in trouble? Yeah, we're still in trouble in the pink sort of way. Well, we'll have to live with that during this first session, and then maybe during the 15-minute first break we can try to remedy it. So that's been a quick run through on problem set number one, and I can show you also the sorts of things that are in problem set number two. The first problem is another one of these paradoxes. Monty Hall is sometimes thought of by some people as a paradox. There's nothing paradoxical about how it comes out, actually, but this one looks like a genuine paradox. So, and it turns out we can use Bayes' theorem to completely debunk the paradox. So you are now playing the following game against an opponent, with the referee also taking part. The referee has two envelopes, numbered 1 and 2 for the sake of this problem, but when the game is played, the envelopes have no markings on them. And without you or your opponent seeing what she does, she, the referee, puts $M in envelope 1 and $2M in envelope 2 for some number M that's positive. And we're going to treat M as continuous in this problem, even though in practice, of course, it would have to be rounded to the nearest dollar or penny or whatever. Now, you and your opponent each get one of the envelopes at random, and you open your envelope secretly, and you find X dollars in it. And your opponent also looks secretly in her envelope. And then the referee asks both of you if you want to trade envelopes. Now, let's think about it from your point of view. You reason, at least naively, that if you trade, you'll get either X over $2 or 2X, each with probability of half. And that makes the expected value of the amount of money you'll get if you trade equal to the weighted average of those two things. Probability of half times X dollars over 2 plus probability of half times 2X dollars. And look, that comes out 5X dollars over 4, which is bigger than what you have now. And so according to that line of reasoning, you should switch envelopes. But the paradox, of course, is that your opponent is equally capable of making the same calculation, and she also has a powerful desire to switch envelopes, and you can't both be right at the same time. So what is wrong with that calculation, and how to make a correct calculation? That's what this problem is about. There's a secret assumption that was made when you think about things from the Bayesian point of view that makes that expected value calculation incorrect. And pretty interesting to figure out what's going on. So that's problem one. Problem two is about exchangeability, which we were just talking about last time. And this is an example that will help you learn about the difference between independence on the one hand and exchangeability on the other hand. So suppose y1 and y2 are identically distributed Bernoulli random variables with success probability theta that's strictly between 0 and 1. Show that independence of y1 and y2 implies exchangeability, but not the other way around, which is something we talked about last time. The simplest way to do this is to specify their joint distribution by making a little 2x2 table that cross-tabulates y1 against y2, labeling all the probabilities symbolically, and then you have to ask yourself the question, what does this table have to look like in terms of theta if y1 and y2 are independent, and what different story does it have to look like if they're exchangeable? And so you'll discover that your intuition about what exchangeability means versus IID is sharpened by working through that problem. And then part B says, can you give another simple example involving a comparison of random sampling? Oh, and we want to talk about that today. I spoke rather loosely about the idea of random sampling last time, but strictly speaking, if you have a finite population you're interested in learning about, like the collection of people around in the catchment basin around the Dominican hospital who are similar to the patients in our heart attack case study, then there actually, if you were going to take a random sample from that population, there's actually two ways to do it. You could take the random sample in a manner that people call at random with replacement or at random without replacement. So basically, you choose one element from the population at random, and you write that number down in your sample. And now you have to decide, do I put that element back in the population again before shuffling them around and then choosing another one at random? And the approach called at random with replacement, that has a special name in all of statistics, Bayesian or not. That's called independent identically distributed sampling, IID for short. At random with replacement. The independence comes from the fact that each unit in the sample was chosen probabilistically independently from each other unit. And the identically distributed part comes from the fact that having put each unit back before choosing the next one, the probability behavior in the population is identical each time. And so IID, independent identically distributed sampling, that's the same as saying at random with replacement from a population. Whereas the other method, in which you don't replace the element chosen each time, has a separate, wholly separate name. It's called simple random sampling, and that's a jargon for at random without replacement. Intuitively, which of those sampling methods seems like it would be more informative? I give you a choice. I'm going to choose a sample size little n from a population of size capital N, where capital N is bigger than little n. And I give you a choice. You can either do the sampling in an IID manner or a simple random sampling manner. Which one seems like it would be more informative? Yeah, simple random sampling. How come? And another way to put that is with independent identically distributed sampling, you run the risk, although it may be small, of getting the same unit over again more than once. And if you do that, you don't learn anything new because you already sampled it before. And so you maximize your information content in these two approaches by working with the simple random sampling approach. However, suppose that little n was very small compared with big N. Suppose your sample had 1,000 records in it and the population had 1 million. Then does the distinction between these two sampling methods matter very much intuitively? If you're only taking 1,000 numbers out of 1 million, then the chance of getting the same number twice in the IID story is really, really small. And so when little n is a lot bigger than or rather, when little n is a lot smaller than big N, SRS and IID are virtually the same. So we could add that to today's notes. When little n, which is the sample size, is a lot smaller than, and most people in math do that by writing not just one less than sign, but two less than signs next to each other. So that means is a lot smaller than. When little n is a lot smaller than big N, the population size, when that's true, simple random sampling and IID sampling are approximately the same. And the reason I bring this stuff up is that when you're actually doing sampling from a finite population, people tend to make the sampling using simple random sampling. But then when you start doing the arithmetic with simple random sampling, you'll discover that the probability calculations are harder with SRS than IID because the population changes each time. You take a unit out, and now you have to work with the population conditional on what you got the first time. And so the math is harder with SRS. But you can have your cake and eat it too. When the sample size is small, is smaller than the population size, you can take the sample in an SRS fashion and then use IID calculations to figure out what's going on, and that'll give a good approximate answer. So that's a distinction that is worth drawing. And so this homework problem says, give an example involving the distinction between with and without replacement from a finite population to think about the difference between IID sampling and exchangeable. And the third, pardon? Oh, thank you. Thank you so much for that. And the third problem is a lot like the one we're going to work on in the next case study, the one about integer valued outcomes and Poisson modeling. So I'll get to that one when we talk about that later on. Okay, so you're now, I think, completely oriented to um, the um, the new stuff on the web page, and I would like to talk a little bit about Bayesian spam filters because it connects nicely with what we spoke about last week involving Bayes theorem and odds form and Bayes factors and so on. Um, you may recall there was a period of time, I'm not sure if the spammers are still doing this because my current spam filter never shows me any of these messages anymore, in which your emails looked like the following. So for a period of time until I got a better filter, I often got emails that looked like this. The email said, effluvium, instant, amarillo, blackfeet, coffin, sommelier, Budapest, rupee, free, chutney, boisterous, immobility. It was filled with about 500 words like that. And mixed in with those 500 words was a URL to a website that sold Viagra. And the idea behind the spammers was they wanted to create a text narrative about what's going on in the email that made it look to the spam filters like it wasn't really spam. And so how could it be that by surrounding your URL to the Viagra place by a series of words like the ones I just mentioned to you, how could that fool a spam filter? Well, one way you might build a spam filter is to look at each word and ask yourself via Bayes theorem, what's the relative plausibility for a given word that it came from spam versus non-spam? So a word like Viagra or penis enlargement or any of those things that they put in these spam emails, those have a very much higher chance of being in an actual spam message than they do in an ordinary message. Whereas, of course, words like the ones I just mentioned to you, like effluvium, instant, amarillo, blackfeet, coffin, and so on, are much more likely to have come from non-spam. So basically, the people who wrote those messages were trying to defeat any spam filters that were trying to use Bayes theorem to process the words in the message. Each time you would do it sequentially. You'd look at the first word. Maybe you'd start out with prior odds of 1 to 1. It's either spam or not, which is actually giving the spammers more credit than they deserve. But then the first word comes along, and you have a Bayes factor for it. A word like effluvium, for example. The Bayes factor for that is modestly strong in favor of this not being spam. So you multiply that in sequentially times the original prior odds. Then the next word comes along, and you model that in the same sort of way. What you really should do, as you know from the way Bayes theorem works, as we saw last time, is you should work out the conditional probability that you see the word instant in the email, given that the word effluvium was already there. But if you've ever heard the phrase naive Bayes in any work you've done, a very powerful simplifying assumption, which can often lead to quite bad results, but a very powerful simplifying assumption is to pretend that all of the information in all the words in the email is independent one to another. And if that were true, then you can just chain along sequentially, adjusting the Bayes factor with the new Bayes factor for each word, adjusting the current posterior odds up and down. Yes, yes. That's exactly right. And this kind of spam filter doesn't pay any attention to that. You're exactly right. It only looks at the email like a bag of words without looking at anything to do with the order in which those words arrived. And again, if you were trying to do a more sensitive spam filter, you would never put that in, right? Because this is obviously not how regular humans write. But I have a page here somewhere toward the back of last time's handwritten notes in which I wrote out what's going on. So let me try to find that page for you. Yeah, it's page 22. Or perhaps it starts on page 21. Yes. So let's switch back over here at the peril of my once again forgetting that I did so and look at, this is the bottom of page 21 in last time's handwritten notes. There's a direct analogy when you're thinking about processing for spam in this way between our HIV and ELISA example on the one hand and spam and not spam on the other hand. So the thing that plays the role of the unknown is whether the email is spam or not. And that's just like wondering whether that guy was HIV positive or not. That's like our thing we called A, the unknown last time. And the thing that acts like data is what the spam filter says about the email, and that corresponds to ELISA as a diagnostic test. So that's our capital D. And so Bayes factor in odds form says, well, the posterior odds in favor of spam given the data over not spam given the data are equal to the prior odds, which, as I said, you might begin by setting to 1 just to create a sort of level playing field if you want. And then the next term is the Bayes factor, and it's the ratio of the chance of getting this particular data set if it were spam to the chance of getting this particular data set if it were not. And that number there is something that can be updated sequentially word by word if you assume the naive Bayes assumption, which is not necessarily a good thing to do, but it's certainly a very fast thing to do. So page 22 of those same notes. Well, what is the data set given spam? The data set is a collection of words. Like this gentleman said, it's a bag of words in which we don't pay any attention to the order. I can write them down in any order I want by thinking of them exchangeably, which is not a good model for how humans write email, but it's an okay model for trying to create a fast robot for looking for spam. And so word 1, it's the probability that word 1 occurred in the email and word 2 ... down to and word k, given that it was spam. So the actual calculation you have to make, chaining along with the chain rule for and in conditional probabilities, you have to go the chance of W1 given S times the chance of W2 given W1 and S times the chance of W3 given W2, W1 and S, and so on. You have to chain along like that. But that's very hard and you'd have to have a tremendous amount of data to be able to do all those conditional probabilities. How many emails are there out there that have the word effluvium in them? That would have to be your denominator right here. How often amongst emails that have the word effluvium in them do you also see the word Amarillo? That would be what this is like. But the naive Bayes thing to do would be to say, I'm just going to pretend these words are all independent of each other, which is actually a rubbish assumption to make, right, from a lexicographic point of view. But it makes for a very fast filter, and the result then becomes simple product of all of those things. That creates the numerator, and similarly for the denominator. So you can very quickly chain sequential Bayes factor that updates each time. And essentially what these people who were spamming used to do, when that was how a lot of spam filters worked, was they were trying to overwhelm the Bayes factor with a lot of words that almost never occur in spam, and then stick in something that does have something to do with spam as the real stinger for their actual message. Well, it's actually trying to take the data and it's trying to create a data set that has the property that even though the email is actually spam, this naive Bayes sequential updating thing with Bayes factors would say it was not spam anyway. That could be one way of thinking about what's going on. That's right. But it requires an intimate knowledge of how the spam filter works, and that's how these people were able to succeed for a while. They knew that there was a generation of spam filters that was based upon the sequential Bayes updating with the Bayes factors. And so they said to themselves, oh, now I'm going to figure out how to generate email messages that will defeat this mechanism, and this is how they did it. Much better idea, but we're talking about 10 years ago now, and also it's a lot harder. So I'm not defending this approach. I'm just saying that this is one method that was used for a while, and that's why those emails came out with all those strange words in them. Now, here's an example of a situation where that was an especially bad thing to do. The assumption of independence when it isn't actually present. Have any of you ever looked at the literature on trying to judge whether nuclear power plants are safe or not? Is this something that's ever come up with you? There is a very famous document in the history of nuclear power safety called the Rasmussen Report. And I wanted to tell you about that for a second because it's an example of exactly the same mistake of trying to do naive Bayes. So Rasmussen Report, and you can just use that as a search string, and you'll find out lots of interesting stuff about this. And so this is about nuclear power safety. So this report was commissioned by the U.S. government at a time when there had not been any major nuclear power accidents in America. I think 3 Mile Island was the first one in our country. Is that right? The nuclear power industry started as an industry to make electricity out of nuclear power in the early to mid-1950s. not long after the atom bomb itself was invented, it was turned to peaceful use as well as to military use. And the industry was able to get by from the mid-50s right until 3 Mile Island without a serious accident. When 3 Mile Island was in the late 70s, if I'm remembering correctly, something like that, 1979 or sometime like that. So they actually were able to get a clean record for 25 years or so. And yet people kept wondering that as we built more and more of these things and no accidents had happened, what's the chance of an accident happening? And so this is a hard problem because it's a no data problem. What's the chance of something happening that's never happened before? You can't use the frequentist approach for this at all. And so they had to use Bayesian reasoning. And so the way they used Bayesian reasoning was they brought together a panel of experts and they had them try to deconstruct a power plant into a flow chart of the form, if this bad thing happens, and this other bad thing happens, and this other bad thing happens, and this other bad thing happens, and ... then the following accident would occur. And they created all these different paths that would lead to an accident based upon ANDing a whole bunch of true-false propositions together. And then they tried to assess the separate probabilities of each of those things in order to multiply them together and get overall probabilities. So imagine you want to compute probability A1 and A2 and ... down to and AK, where each of these things is a true-false proposition representing some small thing that was part of a chain of things that could go wrong. Well, by correct conditional probability, you know that has to be A1 times the probability of A2 given A1 times the probability of A3 given A1 and A2, and so on, down to the last one. But if you try naive Bayes, instead, you would remove all that conditioning. You would pretend that all these things were independent of each other. The word naive Bayes, the phrase naive Bayes wasn't invented when they did this. They were the first people to spectacularly get a really bad answer by doing this. And this is could be, in retrospect, look like it was the first example of somebody using what we now call naive Bayes and getting a really bad answer from it. Now, what's wrong with that? Bad things cluster, and moreover, if you do this with enough terms in your chain, you are guaranteed to get a what kind of number? You are guaranteed to get a small number because you're multiplying things that are less than 1 together. And in fact, their chains often went to 50 or 100 different things that had to go wrong in order for an accident to occur. And so the Rasmussen report, by using naive Bayes, they came up with probability estimates of bad things happening that were wrong as risk assessments by a factor of 100 to 1,000. 100 to 1,000 times too small. And so this is a very graphic example of what can go wrong if you don't remember to calculate conditional probabilities in the chaining process. Pretend that naive Bayes is okay, you can get a really crap answer. And an answer, by the way, that might affect people's lives. So that was probably the most vivid example of things going badly wrong with naive Bayes. In this class, we're going to figure out how to do real Bayes, and that will keep us from making the mistakes that arise with naive Bayes. Okay, so I leave the rest of that spam document to your interest on offline, and we'll go back into the document that we worked through last time to some pages through, and pretty soon we'll have our first break. So, oh yeah, thank you. Here we are again. Pardon? Right. Somehow we were hoping for your help to solve a problem in which the screen came out uniformly pink, but now that you're here, it's not pink. So anyway, you remember the case study. I have picked a moment in time just before, at the end of 2005, and I picked one particular hospital of interest to me, the Dominican Hospital in Santa Cruz, and I've decided I'm going to open a time window in January 2006 and watch a stream of ones and zeros appear. And each of these observations is a 1 if the corresponding patient who was admitted to the Dominican Hospital with an admission diagnosis of heart attack died, and 0 if that person lived within 30 days of admission. And there's going to be about 400 such patients, so let's use a round number and think of a sample size little n of 400. And now I want to not only describe that one data set, but I want to do something considerably more ambitious. I want to think not just about those 400 people, but about the collection, that larger collection of heart attack patients who were similar to them in relevant ways, and call that my population and try to infer outwards, to reason outward in an inferential manner from the sample to that larger population. And so we had a little trouble figuring out what that population was last time. But if you're prepared to spot yourself that there is such a population, then we saw that the frequentist model for the data, although we might like each person to have his or her own theta, we can't do that because there would then be n parameters and n observations, and we wouldn't be able to estimate such a model. So not knowing anything about these people, not having any covariate information, who are the older people, who younger, who has diabetes, who doesn't, and so on, your model would be that your frequentist model would be that all the y sub i's, the 1-0 outcomes, are like IID draws from a Bernoulli process in which everybody has the same probability of dying from the heart attack. And then we talked last time about how to do frequentist inference in that approach. And we had two ways to do it. We did the Mr. Fisher's way based upon the likelihood function, and we also looked at Mr. Neyman's way based upon that diagram I showed you involving the population data set, the sample data set, and the repeated sampling data set, in which we thought through the repeated sampling consequences. And having done that, we got a particular answer, which was we thought that the estimate on the basis of the data was that the underlying population mortality rate for patients like those in the sample was about 18%, give or take about 1.9% was what came out of the frequentist calculations. And we were just on the point of making Bayesian calculations when time ran out last time. And I see that it's now time for actually I'm going to go a few more minutes in because we started 5 minutes late. And so let me carry on a little bit further just to get us where we were last time. So you will recall that although there are several different ways to motivate the parallel Bayesian model exercise for data like this, quite different from the frequentist modeling, the way that I wanted to present to you is based upon ideas of that guy De Finetti we've been talking about a bit. And as I said last time, the reason I like De Finetti's approach so much is that even though he was trained as an actuary and turned himself into a statistician, he actually had the soul of an engineer because he said to us, parameters are typically inherently unobservable quantities. They're things that we can't ever know unless we actually track down everybody in the population and do a complete census. So parameters are inherently unobservable, but data, observables, data are something that we can hang our hat on because we actually get to see data values. So he said, what if I try to build my model from scratch, from first principles, focusing only on things that can be observed in the world? Then the thing that's great about that is that things that are observable can be predicted, and you have a built-in feedback loop. You can make a predictive distribution for data you haven't seen yet and compare the actual data values with the predicted ones. And if your predictions are bad, that provides you a basis for figuring out that you need to go back and change the model to make a better predictive model. So that's De Finetti's idea. Don't try to build your model directly on theta, this underlying parameter that we are eventually going to try to do inference on. Instead, try to build your model directly on the data values. And so he wants to construct a predictive distribution for the entire 400 observations. So for him, it would be his, so instead of me, it would be De Finetti, Bayesian predictive distribution based on his information and also his background assumptions and judgments about the precise pattern of ones and zeros that's going to arrive. And we saw last time that that looked like it was a doomed program right from the start because with 400, n equals 400, that's a 400-dimensional probability distribution. And we humans have enough trouble thinking about 2 or 3 or 4-dimensional probability distributions. How are you going to think about a 400-dimensional probability distribution? True, each element in the data vector is either a 1 or a 0, so it's actually not as bad as if they were all continuous on the whole real line. But still, a 400-dimensional probability distribution on 1s and 0s sounds like a very daunting thing to think about. And right at the end, last time, we were just noticing that De Finetti's next observation really simplifies things. Namely, he noticed that if you don't have any information that helps you distinguish one of these patients from another, if there are no covariates, like as I said before, you don't know who's older and who's younger, you don't know who has hypertension and who doesn't, and so on, then your uncertainty has a certain strong symmetry to it. First of all, you are equally uncertain. You have the same amount of uncertainty about patient number 282 as you do about patient number 2. In fact, any two patients you have the same marginal uncertainty about. So that gives you rise to the idea of identical distribution of your uncertainty across all the elements of the data vector. But he also noticed an even stronger thing, which was that if someone unknown to you were to present the data to you in any other order than the one that you would have seen otherwise, your predicted distribution would remain the same. It would have to be invariant under arbitrary reordering of the order in which the observations came to you. And that's a strong thing to have discovered just from the science of the problem, and it makes it possible to draw actually quite strong conclusions. So he called this property of uncertain things exchangeable, and we can use the language of random variables if we want. There's going to be a version of the Bayesian story that doesn't involve any random variables, but since everybody in the room is probably more comfortable with random variables than other ways, we can talk about it that way. So if you think about y1 through yn as like realizations of random variables, the same way we would do as frequentis, then that vector of n numbers is exchangeable if the distributions of the vector written down in one order and then in any other permuted order, pi1 through pi n is any permutation you want of the integers from 1 to n, they remain the same for all different orderings to write things down. And right at the end last time, we were just at the point noticing that exchangeability and IID are not the same. IID turns out to be stronger than exchangeability, because you can show, and in that homework problem, you can explore this some more, that random variables that are IID automatically are exchangeable, but not the other way around. Exchangeable random variables do have the identical distribution part, the ID part of IID, but exchangeable random variables are not independent in a Bayesian sense, because you remember the Bayesian idea of independence is two uncertain things. Your probability model for two uncertain things involves independence of those things if information about one of them does not change your probabilities about the other one and vice versa. And in fact, as I pointed out in this little example here, if I gave you any subset of those 400 ones and zeros, you would actually find that information very helpful in predicting any other subset of those ones and zeros. So in fact, even though those ones and zeros are exchangeable, that represents your uncertainty about them, they're not independent in a Bayesian way of thinking about independence because, in fact, there's information in any subset for predicting any other subset. So exchangeability and IID are not quite the same, and I guess that's probably a good point. That's exactly where we were last time, so let's take our first break. It's 10:06 now, and I want to pick up a few minutes from not having started right exactly on time, so I'll start again at about 10:17 or 18, something like that. Someone was asking at the break about this guy, Richard Cox, I mentioned before, an American physicist who came up with a wholly different way to think about the meaning of probability and derived the basic rules of probability from axioms that had not to do with Kolmogorov-style axioms about probability as a purely mathematical object, but instead the axioms arose from the actual science of the problem, and then out came the rules of probability using, as it turns out, using functional analysis. So the first paper that he wrote on this, it was published in the American Journal of Physics in 1946. That's why we couldn't find it because I had the wrong year. But I'm going to put this on the webpage. And he also wrote a little book called, it's something like The Algebra of Probable Reasoning. Is that what it's called, what you showed me? Yeah, The Algebra of Probable Inference. It's a small book in which he elaborates on what's going on in this paper. And again, those of you who want to go a bit farther into this stuff, you might find it very useful to do so. So I'm going to go ahead and kill that off for now. I'll come back to this guy. But first I wanted to say a little bit more about independence, because it's actually a slippery concept from the frequentist point of view. It sounds like it should be pretty straightforward, but actually it's a little slippery. Whereas from the Bayesian point of view, it's quite straightforward. It has that information narrative that I've shared with you already. So, the definition of independence from the frequentist point of view applies, strictly speaking, only at design time before the data have arrived, because for frequentists, random variables represent potential of what might happen if you were to dip into a data process that you haven't seen yet and see what comes out. And so basically not going into the strict technical definition having to do with sets and functions from sets onto the number line and so on, but instead just thinking about the frequentist intuition of a random variable. It's a process. It's a description of the process of getting data by means that appear to you to be stochastic. And the strict definition of independence in the frequency story is a narrow technical one, that two random variables that you haven't seen yet are independent if and only if their joint distribution can be written as the product of the margins. That's the frequentist definition of independence. It doesn't have a lot of intuitive content to it. But the Bayesian story says instead that either at design or analysis time, two unknown things that you might choose to quantify your uncertainty about by treating them as if they were like draws from a random variable are independent if, as I said a minute ago, information about one of them doesn't change your probability about the other one, and vice versa. So that's a pretty simple intuitive narrative. After the data's arrived, it's actually pretty unclear what the frequentists mean by independence because you've actually got your data values now and you can't think of them as random variables anymore because they're realizations of random variables. So what exactly is going on? And then you can make a little chart, two charts that are helpful to see some of the differences between the two paradigms. So let's talk about both before the data arrives and after the data arrives. And let's make a contrast between the frequency story and the Bayes story. And I'm going to go back to this general situation where theta is something unknown to you and y is some data that you're going to use to try to learn about the unknown. And so for a frequentist, before the data has arrived, theta is always fixed. In fact, for frequentists, theta is always fixed no matter whether the data is before or after. And before the data have arrived, capital Y is thought of as a random variable. You haven't seen the data yet, and so you're thinking of the data you're going to get as like realizations of random variables. Before the data has arrived, you choose to use the machinery of random variables and uncertainty quantification in the Bayesian story to describe your uncertainty about that thing. And so even though both paradigms would agree that the true logical status of theta is a fixed unknown constant, we pretend that theta is like a random variable and that the little y we're going to get is also like a random variable because that way we can use the language of probability to describe our uncertainty about those things. Now when the data's arrived, in the Bayesian story, y is no longer, quote, random because you've seen it already. So y moves over here, and theta is the thing that acts like a random story. And so if you compare the top row of this table with the bottom row of the second table, you see the exact opposite pattern. Frequentists think of theta as fixed, and before the data has arrived, they think of the data as random. After the data has arrived, the Bayesians think of the data as fixed because it's the one and only one data set you're ever going to see. And it's the theta that's as though it were like random because you're using probability to describe your uncertainty. But I'm actually not real sure what to put in this cell here because what do the frequentists think about the role of y, for example? They can't call y a fixed thing because then there wouldn't be any randomness in their probability statements. And yet they can't call it a random thing either because it's already happened. And so the role of y and where to put y in this picture is actually a little embarrassing for the frequentist story. And then the Bayesian story has that simple interpretation that we were talking about before. Okay, so returning to the PDF lecture notes. As soon as you have invented for yourself the idea of what could then be called unconditional or overall exchangeability, right away you say to yourself, well, that's okay, but usually we will have covariance. So suppose, for instance, in the heart attack case study, I actually knew the gender of the people involved, who are male, who are female. And suppose it were true that, and it is true in the medical literature, that the death rate for heart attack is higher for men than it is for women. Then if you had the actual covariate for each person, whether the person was male or female, would it be appropriate to build a model in which your uncertainty about the 400 ones and zeros was totally or unconditionally exchangeable across all 400 people? If you knew who were the men and who were the women, it would no longer be appropriate, right? Because you've got information. So how could we extend the idea of unconditional exchangeability to a situation where we do have covariates? For example, a binary covariate like male-female. What could we do? Pardon? Yeah, exactly. You partition the data into the men on one part and the women on the other part, and your judgment of exchangeability is inside the male subset, and you also have conditional exchangeability given female in the other one, but you don't have overall unconditional exchangeability. So definitely call that partial exchangeability, and I have written on this with colleagues in the past, and we preferred to call it conditional exchangeability. In our language would be that here the the outcome, the mortality outcomes are conditionally exchangeable given gender. And of course, as soon as you start thinking about that, your appetite for other covariates becomes greedy, and you'd like to have another covariate and cross-tabulate that against gender, and now it becomes conditionally exchangeable given gender and the other one, and then the other one, and then the other one. And in fact, all of statistical modeling can be thought of as if you were to take all of our continuous covariates and discretize them, as the process of trying to construct a big 2 by 4 by 3 by 8 by whatever table or array and get down to something that you could call a kind of conditional exchangeability grid. You find the finest level of detail at which inside the cells you're prepared to treat the people as similar to each other, or at least your uncertainty about them as similar, but between the cells there are big enough differences that matter to you. That's essentially what we're always doing in statistical modeling. We're trying to find the proper level of aggregation with respect to covariates at which we have that particular tension. Similarity within the cells of the exchangeability grid and non-similarity between the cells in something like an analysis of variance way. It's a kind of information tree. I think that would be a way to think about it. Yes. Okay. So De Finetti starts out with what seems to us to be an impossible program. He says, think about your 400-dimensional predictive distribution. And we say back, no one can think about a 400-dimensional predictive distribution. And he says, well, actually, I'll point out to you that whatever your predictive distribution is, it has to be exchangeable. And after learning what that means, we say, oh, that's true. But it certainly still seems to me as though you haven't yet pinned down my predictive distribution. All you've told me is that whatever it is, in order to be logically internally consistent, it has to be exchangeable. But then he went on to prove a really remarkable theorem, which is now called De Finetti's representation theorem for binary outcomes. And it actually shows that under one additional assumption, there is, in fact, under exchangeability, only one and only one way to write down your predictive distribution in order that it be logically internally consistent. If you cannot express your predictive distribution in the way I'm about to show you, then there is something wrong with it. It has some logical inconsistencies built into it. And this is a narrative that's going to lead us directly to understanding the relationship between the Bayesian model for this data set and the Frequentis model. So, first of all, he said, I'm going to start with y1 through yn. Those are the ones and zeros I'm going to see. But now he wants us to make a stronger assumption of exchangeability than that. So he says, why don't you think of y1 through yn? This one. Okay. Why don't you think of y1 through yn as the beginning of a longer sequence and let it go on forever out into countable territory. Then that bigger set, I'm going to call it script P for a moment, and I'll explain why in a minute. Then basically he says to you, in order for my theorem to work for you, you have to be prepared to extend your judgment of exchangeability from this part here to the entire thing. And what he means by that, first he has to tell you what he means by exchangeability on an infinite set. He says that your uncertainty about the infinite collective there is exchangeable if exchangeability holds for any finite subset. And so his theorem says, if you're prepared to extend your judgment of exchangeability from the data you're going to see to this larger collective, then there's one and only one way that your predictive distribution can look in order to be logically internally consistent. So let's examine for a minute what he just did by that if. And in fact, it makes a strong connection with the frequency story. Last time, I think you'll agree, if you think back to it, that I did a reasonably good job of embarrassing the frequency story by pointing out that it was kind of hokey to think of this data set as, obviously we can't think of it as a random sample from anything because no one did any random sampling at all. It's just the 400 guys who showed up at the Dominican hospital with heart attack, right? But it's also hokey to think of it as like a random sample from almost any population you could think of because of those reasons we discovered last time. It was sort of hard to figure out how to generalize outward, either in time or in space from the data set itself. And so I embarrassed the frequency story by pointing that out. Now what I want to show you is that the Bayesian story has the same embarrassment. It has equal embarrassment on this point. And that means that this is something that is fundamental to statistical work in science it's a more primitive thing than the distinction between Bayesian and non-Bayesian probability. It just comes up everywhere in science. Because what exactly does it mean when Desfinity says, I want you to extend your judgment of exchangeability from y1 through yn to y1 to y2 dot, dot, dot. It's as though he's asking you to think of your data set, y1 through yn, as like a random sample from that countably infinite collective. Because if it were like a random sample from that collective, then that would correspond to the exchangeability story being extended to everybody else. So assuming that this is true, extending exchangeability is equivalent to thinking of y1 through yn as like a random sample from script P. And so in the same way that we had to, in the frequency story, we had to be prepared to say what was the population that we're prepared to generalize to, that we're going to try to generalize to. In Definiti's theorem, he's making an assumption that the data is like a random sample from that population of whatever was going to be in that list beyond the y1 through yn. You, in other words, you as a scientist have to fill in the dot, dot, dot with words that describe who are these people who are exchangeable with the patients at the Dominican hospital. They are not themselves the patients because you put them in the first block of the data here. So who are these other people? And as soon as that question arises, you're asking and having trouble answering the same question that we did from the frequency point of view. Namely, what is the broadest scope of valid generalizability outward from this data set? Did you have a question or comment? Okay. This is a question which lands upon us as statistical scientists with equal force and equal embarrassment each time we use inferential machinery. Whether that usage of the machinery be Bayesian or frequentist, we have to face the same fundamental question. What is the broadest scope of valid generalizability outward from my data? And right there in the if of Definiti's theorem, which otherwise just looks like some sort of innocuous technical condition, actually it's more of a spiritual condition, you might say, than a technical condition. It's actually really telling us to think about the science of the problem. Who are those people exactly in the part called dot, dot, dot? And as soon as you say who they are, you have now told me what the population is that you're prepared to generalize to. Anyway, his theorem says the following. If you're willing to regard y1 through yn as, let's say, the first little n terms in that infinitely exchangeable binary sequence, let's agree to call y bar n the running mean of the first n observations. So imagine you're seeing these ones and zeros. You stop after the first one and take the mean of itself, the mean of one number since itself. Now stop after the first two, take the running mean of the two so far. Now stop after the first three, take the running mean so far. Stop after n and you get y bar n. It turns out that under exchangeability, the y bar n's have to have a limit. And we could give that limit a name. We could call it theta. And not only does that the same theta that we had in the frequentist point of view, but it also has the same meaning here. Namely, the marginal distribution given theta for each of the yi's must be a Bernoulli, and theta represents the long-run mean of the y's. In other words, theta represents the population mean, just like it did in the frequentist approach. So this limiting value of y bar n has to exist, and it has to be the same as the marginal probability that each person dies, and also has to be the same as the population mean that we were trying to do inference to before. Pretty cool already that right in the beginning of his theorem, which is a theorem about observables, a thing that plays the role of a parameter, namely the same theta we had in the frequency story, appears naturally out of the exchangeability judgment. And moreover, it turns out, I'll skip over most of the technical stuff on this slide. Moreover, all logically internally consistent predictive distributions have to look like equation 15. So what does the left-hand side say? It says, well, this is my predictive distribution for all those n observables. It has to be expressible as a particular integral. And the integral in question is a function, and it's one that we met last week, namely theta to the s, 1 minus theta to the n minus s, where s is the sum of the y's. That was the same thing we found when we talked about things from the likelihood point of view or the sampling distribution point of view, thinking of things as frequentist. So right in there is the frequentist sampling distribution, and it says you multiply that times something which turns out to be a probability density on theta, and you average that over all the theta values from 0 to 1. If your predictive distribution is to be logically internally consistent, then it has to be expressible in that form for some choice of this thing here. And if you think about it, here's the data. The only thing this P of theta thing could be is the prior. So this is actually saying take the weighted average of the sampling distribution that comes from the Bernoulli story that we found in the frequentist approach. Take a weighted average of that, weighted by the prior probabilities, and that's the way you are able to express your predictive distribution. Remarkable that he's able to get an integral representation out of just exchangeability, and that it corresponds directly to the same sort of story we were telling from the frequentist point of view. If we knew what theta was, this would be the sampling distribution for the y1 through yn's. They would behave like theta to the s, 1 minus theta to the n minus s. And the reason that this is a complicated mathematical theorem, I'd like to spend a minute to try to unpack it and tell you what it means in layman's terms, layperson's terms. I already mentioned this important digression 1, the business of thinking of the data as like a random sample from that bigger collective. Important digression 2 is to remind you of something called the law of total probability, because in order to understand how the right-hand side of this equation is working, that the previous equation is working, we have to think about this thing that people call the law of total probability. You remember in the HIV and ELISA example, we wanted to work out the chance the guy really is HIV positive given the data, and that turns out to be P of A times P of D given A over P of D. And we discovered that this thing here was something I called the annoying normalizing constant, because it's hard to compute. But if you look at it, it's actually a predictive distribution, because it says, not having seen any data yet, what do you predict ELISA will say? And the thing we're interested in here is a predictive distribution also, so there ought to be some connection. So the standard way people work this out, you remember last time we had 2 ways to solve this problem, and right now we're going to work out a 3rd way. The one way last time was to be clever and avoid having to compute the annoying normalizing constant by writing Bayes' theorem in odds form and then it canceled. You probably recall that. The other way was to build that little 2x2 table and work out all the different where the blood samples would fall, and we were able to calculate the predictive quantity that we needed just by adding up quantities in that little 2x2 table. But now, let me remind you of something that is an important idea from basic probability. We want to know what's P of D, right? P of D equals question mark. So D is like a blob in the Venn diagram, like usual. And we say to ourselves, this is something as a Bayesian statistician, I say to myself all the time, I don't know what P of D is. I'm having trouble thinking about D by itself. But if I knew what the truth was, if I knew, in other words, D, remember D was the statement that ELISA says HIV positive. So this is, ELISA is going to come out HIV positive. I'm having trouble thinking about that. My life would be made much easier if I could somehow bring into the conversation the truth about whether the guy is HIV positive or not, because after all, this is just what ELISA says. So let's take the overall Venn diagram and let's partition it according to the truth. So over here is the place where the person really is HIV positive, and over here is the place where the person's not HIV positive. The math name for that is a partition, because we divided up the whole Venn diagram into a series of sets which have the property that they are mutually exclusive. They cannot both occur at the same time, and they're also exhaustive. If you were throwing a dart, it has to land either in the A part or the part called not A. And the thing that's nice about having done that is that once we've done that, we can see now how to compute P of D, because you get P of D by adding up this part here together with this part here. So P of D has to equal P of D and A plus P of D and not A. That just has to work. You can see from the diagram that has to work. And then you remember by the definition of conditional probability and how the multiplication rule works, that is the same as P of A times P of D given A plus P of not A times P of D given not A. Those two things are equivalent just by the definition of how the multiplicative rule works. And what we've just done, if you think back to the ELISA case studies, we've now expressed the thing we don't know in terms of all quantities that we do know. P of A was the prior probability of the guy being HIV positive, which was 0.01. So P of not A has to be 0.99. P of D given A was the sensitivity, which is 0.95. And P of D given not A turns out to be 1 minus the specificity, which is 1 minus 0.98. And bada bing. We've just computed the predictive thing by bringing in the truth and then creating this sum. It's a product of the story for the truth, because look what we're doing here. P of A plays the role of that theta in Dave Finetti's theorem. It's the truth about the unknown thing. And D given A plays the role of the sampling distribution. So it's just like this sum gets to be replaced by an integral when instead of the partition having only a finite number of elements in it, it has a countable or uncountable number. So this just reminds us on page 22 of the thing I just showed. And if you look back in your early work on probability, they will probably just talk about this thing and call it the law of total probability. It says anytime you want to work out some probability D and you're having trouble working it out, find a partition and break it out across the partition. And you can always break it out in this form here as a weighted average of the sampling story given the elements of the partition weighted by the partition probabilities. That just always works. And now if we let k go to infinity, this sum gets replaced by an integral. So the continuous version of the law of total probability says that expression at the top of that page, equation 18. If x and y are real valued random variables, you can either model y, and this is important Bayesian insight I'm about to come to. Equation 18 just looks like math, but it actually says something important for learning how to model the world. P of y is the density for y. So if you were trying to model y probabilistically, and you could do it, the left-hand side is how you do it. You would work out the predictive distribution for y, which would otherwise just be called the probability density for y. So if you could do it, you would work the left-hand side. But what if you can't? What if it's too hard to work out the probability behavior of y directly? Then this integral representation here provides an alternative path that allows you to work it out indirectly. And look what the integral says. It says take a weighted average of find an x, first of all. Find an x upon which y depends. And the right-hand side says work out the conditional probability behavior of y given x and multiply that by the probability behavior of x, which is like taking a weighted average or mixture across those things. So the right-hand side says what you want to do is to take a mixture or weighted average of the conditional behavior of y given x weighted by the behavior of x. So that's an example of, there's two different ways to talk about the intuitive content of equation 18. One is to call it a mixing distribution, and the other is to call it, it's trying to tell us a hierarchical representation of what's going on. Because look what the right-hand side says. It says, actually look at the whole equation together. It says, if you're having trouble modeling some quantity y directly using probability, then you can model it indirectly by the following two-step process. Find an x upon which y depends. First model x by itself, and then model y given x, where in the second stage you use the x that you got from the first stage. That's exactly what that integral says to do in ordinary day-to-day language. So I can either model the random variable, the random behavior of y directly through P of y, or hierarchically by first modeling the random behavior of x through its density, and then modeling the conditional behavior of y given x through the conditional density. And what's cool about this is that x and y are completely general in this discussion. Given any quantity y that I want to model stochastically, I'm free to find any x upon which y depends and model y hierarchically given x if that turns out to be easier. And the trick is always to figure out what the x is that makes your job the easiest, that makes the calculations the easiest. And in any situation that involves data and unknowns, and you're trying to predict data, it's always easier to model hierarchically in which you bring in the unknowns first, and then you talk about the data given the unknowns. Because if you knew what theta was, it's not very hard in any problem involving random quantities to talk about how the data would behave if you knew what the truth was. That's like Mr. Bayes noticing that it's easier to talk about the probability of effects given causes. If you know what the right answer is, then it's pretty easy to say how the data should have come out. So P of y is hard in this equation. P of y given x is much easier, because if we knew what x was, it becomes easier to say what y would be. And so you do this thing that Dennis Newley calls, you extend the conversation by bringing in x. It wasn't in there before, but you make your life easier in an indirect fashion by bringing it in, and you do a two-stage argument. You say, first I'll talk about x, and then I'll talk about y given x. And when I put them together in the right way, I get the story for y. And that's completely general. Any x will do. So go ahead and pick one that makes your life as easy as possible. So symbolically, what we're saying is that you can either model something directly, that's equation 19 now, with y, or you can model it hierarchically by finding an x upon which y depends and modeling y, the second stage of the hierarchy, y given x, where you use the x in the second step that you got from the first step. And in fact, if you've ever taken a course on how to simulate from random distributions, how to write code to simulate from distributions, you may have even seen that this is something that they talk to you about. If I want to generate a draw from y, if I know what the distribution is and it's easy to sample from, I can just draw directly from it. That's what the left-hand side of it says. But if I'm having trouble doing it, the right-hand side says, here's how to make a draw from y. Find an x upon which y depends. First make a draw from the distribution of x, and then make a draw from the distribution, the conditional distribution of y, given the x that you got a moment ago. And that will turn out to be a legitimate and valid draw from the distribution of y. And so that's essentially what this hierarchical or mixture or two-step representation is saying to do. And the reason I bring it all up is that it now shows us what the meaning is of De Finetti's theorem. That previous equation that looks so maybe a little weird the first time you saw it, equation 15, which is the heart of his theorem, can actually be expressed. It looks just like one of these mixture things I've been talking about now. The left-hand side says, I want to talk about the probability behavior of y. I'm having trouble thinking about it directly. And so Lindley says, okay, extend the conversation. Bring in something upon which y depends. And instead of modeling y directly, model it hierarchically by first building a model for theta through that prior distribution, p of theta, and then building a model for y given theta, and that's what the sampling distribution is. So in fact, what De Finetti did was this trick based upon the idea of mixtures or hierarchical models. That's what his theorem is trying to say. So, rewriting that equation 15, or reminding us of what it is, in equation 20, the top part of equation 20 is the law of total probability applied to continuous things. But the bottom part is what De Finetti's theorem said it had to look like. So look in equation 20, the right-hand side of the first equation has to be equal to the right-hand side of the second equation because they're both equal to each other. And this has to be true for any probability distribution p of theta. And there's a theorem in functional analysis that says if that's true, then the part called p of y1 through yn given theta has to equal that other part called theta to the s times 1 minus theta to the n minus s. They just have to be the same. And look what that says. The left-hand side of equation 21, p of y1 through yn given theta is, when you think of it as a function of theta for fixed y, is the likelihood function that Mr. Fisher told us to think about in the Bernoulli sampling model. Or you could think of it also as the sampling distribution. And the right-hand side is the sampling distribution for the Bernoulli that we worked out from the frequentist point of view. And so to summarize De Finetti's theorem intuitively, it says the following. The assumption of exchangeability in your uncertainty about binary observables, y1 through yn, amounts to behaving as if the following three-step as if. First of all, as if there is a quantity called theta, interpretable either as the long-run relative frequency of ones in the countable process that you get by extending from y1 through yn out to y1, y2, ... or the marginal probability that any one of those y's would be 1. Secondly, I have to treat theta like a random variable, having a density p of theta. And thirdly, conditional on this theta, the y's have the same distribution that they did when we were thinking the world in a frequentist way. So in yet other words, and this is the principal takeaway here, for a Bayesian whose uncertainty about binary y is exchangeable, the model may effectively be taken to have the simple mixture or hierarchical representation. And in fact, later on we're going to talk a lot about hierarchical models, but actually all Bayesian models are hierarchical models because they all have this two-layer story. You start at the top layer by building a probability model for the unknown thing. That turns out to be the same as specifying your prior distribution in Bayes' theorem. So here's our opportunity to bring in all the information we have about theta external to the data set. And then in the second layer, if you knew what theta was, the yi's become conditionally IID from some distribution you've met before, like the Bernoulli in this case. Later on, it's going to be the Poisson or the normal or the whatever, but that's the basic story. All Bayesian models are going to have this character. Put a prior on the unknown parameters, and then conditional on that prior. All parametric Bayesian models are going to have this character. Put a prior on the parameters at the top level, and then the second level hierarchically goes. Pretend for a moment you know what the parameters are. Then the sampling distribution for the y's given that, the y's will be IID from some distribution you've met before, like the normal or the Poisson or Bernoulli. So we have now started with a model for our uncertainty about things we can observe in the world. This is the beauty of DraperBayes' story. And that turns out to be functionally equivalent to a beautifully simple hierarchical representation of how a Bayesian model should unfold. And it tells us that we have to be prepared to bring in information external to the data set through that prior distribution P of theta. And this is the link between frequentist and Bayesian modeling of binary outcomes, and it also turns out to be a similar link for other more complicated data processes. Exchangeability implies that I should behave like a frequentist as far as the likelihood function or sampling distribution is concerned, taking the yi's to be IID Bernoulli theta. But you have to be like a frequentist who treats theta as a random variable with a mixing distribution P of theta that can be thought of as the prior. That's where you bring in the external information. And this becomes the first example we will see over and over again of a general fact that exchangeability by itself does not imply IID, but it's equivalent often to conditional IID. So the assumption that the yi's are exchangeable turns out to be functionally equivalent to the assumption that the yi's are conditionally IID given one or more parameters. And that's how you get this link between exchangeability on the one hand and the kind of parametric model we see at the bottom of this page in equation 22. So exchangeability is actually a special kind of conditional independence. Binary exchangeable yi are not independent, but they become conditionally independent if you knew what the truth was. And the thought experiment that I'd like us to go through, if I haven't already done this one, I don't think I have yet, goes like this. You and I are watching a Bernoulli process unfold, and we both agree that what's going on, it's as though there's a machine on the table here, and I press a button, and a 1 or a 0 comes out, and I do that over and over again. And we both agree that a good model for what's going on inside the machine is that the resulting numbers are conditionally IID given some theta. Now, case 1, you don't know what theta is. I tell you that in the first 10 outcomes of pressing the button, 7 of the outcomes came out 1s. Is that information helpful to you in predicting the 11th one? If you don't know what theta is, would you like to use the outcome of the first 10 realizations to help predict the 11th one? Massively helpful. But now, if down from the sky on a stone tablet comes the statement, which we're now supposed to regard as truth, that theta really is 0.6, is there information in the first 10 realizations that helps you to predict the 11th one? If you know that theta is 0.6, is there any information in the first 10 observations that helps you to predict the 11th one? Well, if the data really are conditionally IID Bernoulli theta and theta is exactly equal to 0.6, then the first 10 observations give you no information at all about the next one because you know the next one is Bernoulli theta with theta equals 0.6. You knew ahead of time that the 11th one was Bernoulli theta, but you didn't know what theta was. And not knowing what theta was, the first 10 observations give you a lot of information about what theta is. But if you knew what theta was, there's no information at all in any data values. And that's a remarkable fact. In fact, there's a little picture that I've drawn in one of these pages that I want to share with you. Thing will ever come up. Okay, good. This is a pictorial description of the value of being able to assume conditional independence when it's appropriate to do so. The little diagram on the left is a diagram describing the relationships amongst 5 y's, y1, y2, y3, y4, y5. And I'm going to use this is an example of a graph, actually. It's an undirected graph. So I'm going to use circles to represent, they're so-called nodes in the graph, and circle means it's something you haven't seen yet that you're wondering about. And lines represent the assumption that these circles are related to each other probabilistically, by which I mean that there's information in one of these circles for helping you to predict another one. If all you know in this Bernoulli story is you don't know what the theta is, but there is a theta hidden behind the curtain, then all you can assume about the y's is that they're exchangeable. And in fact, the graph is very complicated then because each y has information for predicting all the other y's. So see how there's going to be, every single node is going to have lines from it to all the other nodes. And so if I were to, in fact, I'll extend this notation A solid line with no arrows on it is going to mean that the two nodes are related. And an arrow pointing from one node to another means that one of them is causing the other one, in the sense that information about A definitely helps you to pin down B. And so what you notice on the left-hand side is that when all we assume is exchangeability, the graph is complicated because every pair of nodes has lines between it. And if you count all the lines, when n is 5, there's actually 5 choose 2 different connections in this graph. And that's, you know, remember, n choose 2 is the same as n times n plus 1 over 2, which here turns out to be 10. But the important thing is that that's order n squared. And so if all we know is exchangeability, the graph has complexity order n squared, because all the nodes have to be linked to each other because they all have predictive information for each other. But now if, like one of these deus ex machina things, like I keep saying, down from the sky on a stone tablet comes the truth about theta, then theta acts like a causal agent for all these other ones. And if you knew what theta was, it drives all 5 of the other ones, in the sense that you could simulate them all only based on the knowledge of theta. And all those connectors between the y's disappear. Because if you knew what theta was, then there's no information in the y's for predicting any of the other y's. And look what that does. The complexity of the graph has been reduced from order n squared down to order n. So that's what's cool about conditional independence. When it's appropriate to assume it, it causes a tremendous simplicity in your Bayesian models. You go down typically from order n squared graphs, which are much harder to model and simulate, because you have to be thinking about the joint dependence of all these things with each other, down to something that's only order n, and your modeling task is far easier. So back to the slides. Equation 22, this simple hierarchical model, is our first example of something that's going to come up over and over again, all quarter long, or rather all course long, namely that we will find ourselves all the time starting out wondering how to model the predictive distribution, as in the left-hand side of equation 20, and saying, I'm actually having trouble coming up with a good probability model for the left-hand side of equation 20, the predictive distribution, but it turns out to be equivalent to this hierarchical model, which is much easier. It breaks my task down into 2 things. I model the information about theta external to the data set through the prior in the first row of this hierarchical model, and then I use the fact that having pretended that we knew what theta was, the yi's, which started out a minute ago just being exchangeable, now become conditionally dependent given theta, and in fact they're IID, and I can use the same kind of sampling distribution that I would have from the Frequentis point of view. And so this is a little smaller version of that little chart I showed before. Let's go on to this section now called 2.4, prior, posterior, and predictive distributions. Strictly speaking, in Definity's theorem, this thing at equation 15 back here, strictly speaking, P of theta is just a mixing distribution mathematically, but we can do better than that because we can think about where the information comes from in the problem. So like it says here, P of theta doesn't involve the data vector at all, and yet it clearly is a distribution that's quantifying information about theta, so it has to represent your information about theta external to the data set, and we've agreed already to call that your prior distribution for theta. And in a minute, a few minutes, we'll see how to specify such a prior. Second question, if P of theta represents my information external to theta, what represents this information after y has been observed? And evidently, using the logic of Bayes' theorem, it has to be P of theta given y. It becomes the conditional distribution for theta given how y came out. That's your information after the data has arrived. And because of the temporal story about prior and posterior, a priori, a posteriori, before and after, everybody calls that thing the posterior distribution, even though a better name for it would be something like the total information distribution. It brings together all information, both internal and external, to the data set. And then the last implementation question, how do you get from the prior to the posterior? How do you update your information about theta in light of the data? And the answer is, it has to be some version of Bayes' theorem, except for continuous quantities. And so you remember what Bayes' theorem looked like when we were talking about true-false propositions. It looked just like this, except theta was a true-false proposition A, and y was a true-false proposition D. If you take those and substitute them directly, we get what we had before as Bayes' theorem for propositions. So that one question becomes, do I get anything that's meaningful by just taking the old basis theorem and sticking in actual quantities that are more complicated than that? Does it become sensible? In this equation here, theta is a real number living between 0 and 1, and little y is a vector of n observations, all of which are binary. And so this is a number, and this is a vector. That's more complicated than Bayes' theorem, when each of those things inside the conditional probability story are just true-false propositions. So you could ask yourself, does the Bayes' theorem work in this more general context? And it was Laplace who showed that it does. You just write down the same theorem you would have written down with propositions, and you start sticking in more complicated objects in place of the propositions, and the theorem still works. Except that you have to do a bit more work to explain, to interpret the ingredients there. So let's see what's going on. The left-hand side of equation 24, once the data has arrived, we are going to think about that as a function of theta for fixed y, because in the Bayesian story, unlike the frequency story, you don't have to think about other data sets than the one that you happen to get. In fact, than the one and only one data set that you're ever going to see. All you have to think about is the data set you've got. And so once y is in the book, so to speak, the left-hand side has to be interpreted as a function of theta for fixed y. That being the case, the right-hand side also has to be a function of theta for fixed y. And right away, the first implication of that is that the denominator in equation 24, if the entire right-hand side is supposed to be a function of theta for fixed y, the denominator on the right-hand side just has to be a constant. It has nothing to do with theta. And so that's another reason I call it the normalizing constant. It's just stuck in there. 1 over p of y is just put in there as a constant c to make the left-hand side add up to 1. And so that's the new analog of the annoying normalizing constant that we had before. And notice it, again, has a character of a predictive distribution. Now, p of theta, well, that's just the prior, so we know what that is. But now look what happens to p of y given theta. If the entire equation is to be interpreted as a function of theta for fixed y, then I have to look at that object called p of y given theta and reinterpret it as a function of theta for fixed y. But who pointed that out as a good thing to do? You take the sampling distribution, p of y given theta, and you reinterpret it as a function of theta for fixed y. That was Fisher's idea in his approach called maximum likelihood that we talked about last week. You take the sampling distribution, and you reinterpret it as a function of theta for fixed y. Before any data has arrived, p of y given theta, if you pretend that you know what theta is a description of how the data will come out. It's a function of y for fixed theta. But after the data has arrived, Fisher pointed out that it's better to take that same object and think of it instead as a function of theta for fixed y. And actually, as I said before, actually it wasn't Fisher that did that the first time, it was Laplace who did that. In fact, practically everything that was named for somebody else later on, Laplace did first. And the problem was just that he wrote about it in French, and the people who were doing statistics and probability in England were too uppity to read anything in French in those days. And so no one knew for a long time that Laplace had done all these wonderful things. In particular, Fisher got a lot of credit for maximum likelihood, and it was only much later in his life that it was pointed out to him that Laplace had done it first, and Fisher had a tremendous ego, and he basically said to that, that's too bad. He might have done it first, but he didn't talk about it very much, and I talked about it a lot, and so I'm the one that gets the credit. That's essentially what Fisher said. Have I talked about Stigler's law of eponymy with you guys? This is way an example of that. Okay, so now we know what to do. Actually, we agree with Fisher. The likelihood function is important because we take that same sampling distribution that Fisher was interested in and we reinterpret it as a function of theta for fixed y. And following Fisher, we call it the likelihood function. It's the same object that he was interested in, except now the cool thing is that we're thinking of theta as like a random variable. So for Fisher, it was just a function of theta to be maximized. Remember that's how we did it last week. But for us, it's a density. Actually, it starts out being a non-normalized density, and we're allowed to use the normalizing constant to normalize it if we want. And so what this suggests is that p of theta given y is a density in theta, p of theta is a density in theta, and L of theta given y is also a density in theta. And basically what Bayes' theorem says to do is you take two densities and multiply them times each other, point by point for each theta, and that'll give you a curve which doesn't necessarily have area 1 underneath it, and so you just work out what the area is and divide through to normalize it so that it has total area 1, and that's what the normalizing constant does. So pretty cool. So Bayes' theorem says, okay, write down your prior. I haven't said yet how to do that, but write down your prior. So here, the unknown theta, I need to go over here, don't I? The unknown theta lives between 0 and 1. So I write down my prior. I haven't said what it is yet, P of theta. And I write down my likelihood function, theta given y, which is simply the same as the sampling distribution for y given theta, possibly with some normalizing constant in front of it. And I write that down also. And all you need to do to work out the posterior distribution, which is P of theta given y, Bayes' theorem says you take whatever curve is here and whatever curve is here, and you multiply them times each other in vertical slices, point by point for theta. That'll give you a third curve down here. Work out its area underneath it, divide through so that it is a proper density, and that's how to update your uncertainty. So it's going to turn out in this problem that the likelihood function looks like this. In fact, we've seen that already. We saw it last time. It's highly concentrated around the number 0.18 in our data set with 400 observations where the number of people who died was 72. It turns out that y bar, which is S over n, the maximum likelihood estimate, is 18% mortality. So that was the background of our data set here. And as we saw last time, that's what the likelihood function looks like when you draw the whole unit interval. It's highly concentrated around 0.18. And by the way, it looks like a normal curve. And you guys agreed with me on that last time. Earlier, Fisher would have really resisted you saying that because he only wants to think of it as a function of theta for fixed y that should be maximized. As soon as he allows it to be thought of as a density, he's being a Bayesian, and he didn't want to be a Bayesian. Remember, he threw out the prior distributions along with John Venn and had to suffer the consequences. But now we can think of it as like a density, because it is. Suppose it turned out that you didn't know much about theta external to the data set. Theta, after all, is the underlying mortality rate for heart attack people at the Dominican hospital in the middle part of the last decade. You guys probably don't know much about that. I know a little bit more than you do because I live in the Santa Cruz area, and I'm going to show you one particular quantification of prior information that's based on the fact that I've lived in the Santa Cruz area for 10 or 11 years now without ever having heard that the Dominican hospital is either really, really good at what it does or really, really bad at what it does. And so that actually is information that tells me that theta, the underlying mortality rate for people like the heart attack patients at the Dominican hospital in that time window, is probably not really close to 0, and it's probably not really close to 1. And so that's actually information I can use to sharpen my posterior inference, at least a bit, if I wish to. But you guys, if you don't know much about theta, how would you express with a probability distribution the idea that you don't know much about theta? You might well use a uniform distribution. So this is a way of saying don't know much about theta. And we agreed last time, I think we agreed to call a prior like that diffuse. Did we use that word before? Diffuse. Maybe this is new. Clearly, one name for this prior is flat, because it is literally flat. Another name for it is diffuse, because actually the diffuse means it has a lot of spread to it, and actually that's quite a spread out distribution on the unit interval. Some people call distributions like this non-informative, but I don't like that term, because actually every prior distribution carries with it one information source or another. So I'm not going to use that term. I'm going to call priors like this diffuse or flat. Well, you tell me what the math says to do. If I multiply a constant function times another function and go down and see what the product is, what's it going to look like? In other words, if I multiply a flat prior times the likelihood function, the posterior is going to do what? It's going to be the same as the likelihood function. And so in the special case, when the prior is diffuse like that, it's going to turn out that the posterior distribution looks just like the likelihood function. And so it's going to turn out that Bayesian and non-Bayesian inference is going to be similar, because the posterior is just like the likelihood function, and Fisher was using this information source, and we Bayesians would use the same information source. So Fisher's maximum likelihood is a special case of the Bayesian story when the prior information is relatively diffuse. In fact, this picture here with a flat prior is the basis of what Fisher later on called fiducial inference. And he was very crusty. He wouldn't admit that when he was wrong or just doing something somebody had already done. But fiducial inference just turns out to be Bayes with a flat prior. And he finally at the very end of his life in private conversations, he was prepared to admit that, but never in public. Okay, so that's the basic story. Write down the prior, write down the likelihood, multiply them in little vertical strips, renormalize. That's your posterior. That's Bayes' theorem for continuous quantities. And you can also readily construct the posterior predictive distribution for the prior predictive distribution for the y's before they're observed, or for future y's once some of them are known. And so let's go through the logic of that, and that'll bring us up to our next break, I think. Suppose you got to see the first m of the observations, where m is some number smaller than n, and you wanted to construct the predictive distribution of ym plus 1 dot 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 down to yn given y1 dot 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 down to ym. The prime moment to try to use the insight that we learned from de Finiti's theorem. I say to myself, is that thing on the left-hand side of that equal sign, is it easy to work with? Is it fun? Can I go at it right directly? And right away I notice it's not. I'm having trouble. So now I use Mr. Lindley's idea, which is built into de Finiti's theorem. What was our trick? If you're having trouble modeling something directly, you model it indirectly by bringing in something upon which it depends. And the outstanding thing in any model like this upon which the data depends is the truth, right? So you want to bring theta into the narrative. And so Lindley says, okay, extend the conversation by bringing in theta. So I'm going to go ym plus 1 dot 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 down to yn. And I'm going to extend the conversation by also bringing in theta. And the only way to do it correctly with the rules of probability is to bring it in on the left-hand side of the conditioning bar. So y1 through ym. And what you're supposed to do is you're supposed to add that up over all values of theta. And the left-hand side is equal to the right-hand side. That's another statement of the law of total probability. That's like that thing, the Venn diagram I had with the partition sets. That's just basically another version of that. Now, that doesn't look like progress yet because the thing that we're integrating is still hard to do. But actually, it's pretty close to progress because the next step in the narrative is I want to move the theta to the other side of the conditioning bar. If I can get it over there, then I can really start talking because I'd be able to say something about future data values given that you knew what theta was. So the standard trick here is just to force it over there where you want it to be and then see what you have to stick in to make it work. So let's do that. Ym plus 1 through yn given theta and y1 through ym. And it turns out that you can get the right answer by timesing it by a particular quantity and then integrating. In other words, the product of this times this is equal to this. And you can equate these two things to each other and solve for what that is and see what it is. And it turns out to be a familiar friend, P of theta given y1 through ym. What would be our name for that thing in the box? Is it a prior distribution for theta? No, it's based on data. So it's some kind of posterior distribution, but posterior based on what data? Based only on the first m values. And so basically, if you run Bayes' theorem on the first m values with whatever the priors that you have, you'll get out this posterior. So that's something that's calculatable as soon as you specify what the prior is. And now comes a really important step that's based upon that insight you guys told me a minute ago about the machine that spits out the ones and zeros. Look at the first term there that I'm multiplying by that posterior. It says, please predict for me the next observations from m plus 1 to n, if I give you the following information. I give you the truth, and I also give you y1 through ym. So now, once again, we're in that situation with the block of stone coming down from the sky, right? If I tell you what the truth is, and I also tell you the first m data values, can you simplify that? You throw away the data, right? Because if you knew what theta was, the actual data values, the first m data values, are completely irrelevant. Because theta tells you about the future behavior. No matter what the past data was, it was just random fluctuations around the true theta story. And that equation says you know what theta is. So very cool. By the logic of that story we just said a minute ago, you get to throw that data away, and now this becomes something where both things inside this expression are interpretable. This is just the sampling distribution for the next m plus 1 through n observations. Sampling distribution for ym plus 1, dot, 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 up to yn. And this is just the posterior distribution for theta given y1 up to ym. So we now have the thing we wanted, this predictive distribution, expressed in a particular integral form. And if we actually step up to the plate and specify a prior distribution, we can use Bayes' theorem to create a posterior distribution right here. And then we have to hold our breath really nicely or go find a package like Maple or Mathematica and try to work out what the integral is. And if all the smoke clears and the integral has a nice closed form expression, then we get the predicted distribution. Otherwise, as we're going to see later on, if it doesn't have a closed form expression, there's still going to be very nice ways to learn about it by simulation, by making random draws. So that's how you construct predictive distributions. You use that basic trick that if you know what the truth is, you get to throw the previous data away because it doesn't give you any new information if you knew what the truth was. So let's take our second break. I'll start again at 11:30. So we have, I've probably frustrated many of you so far by speaking about these examples in a rather abstract way, and I hope to remedy that right now because we're going to get into the nuts and bolts of how to actually specify the prior distribution in this problem. We have seen a remarkable thing in specifying the sampling distribution. De Finetti's theorem says in this problem that if you start with the judgment of exchangeability about your uncertainty, then there is one and only one correct sampling distribution in this problem, namely the Bernoulli, IID Bernoulli theta. But the story about logical internal consistency, the story about De Finetti and so on, it doesn't say anything about how to specify the prior. And also we'll see when we start on the very next case study involving integer valued outcomes that the wonderful security provided by De Finetti's theorem in the binary case, namely that exchangeability leads directly to one and only one sampling distribution, unfortunately that security disappears. As soon as you leave the world of binary outcomes, things are harder, and you don't have a unique specification of the sampling distribution, and you certainly don't have a unique specification of the prior. So as I was discussing with someone over the break, this last break, you can regard, you may have seen in my intro to the class that was advertising it, the statement something like, this is a very simple paradigm. You put in 4 ingredients and you process them with only 3 equations, and that solves all of the problems in inference and prediction and decision making. But what I tried to say also in just words, and now we're going to see how this unfolds in this case, in this course, is that actually figuring out how to map intelligently from the scientific or engineering problem you start with to those 4 ingredients can take a lifetime. That's the part that is the delicate part, the part that requires, it's a combination of art and science, a combination of judgment and rigor. So we have already begun to see that there are some special cases where the specification task is less burdensome. Here it is De Finetti with dichotomous outcomes. You don't have to worry about the sampling distribution. It comes right out of the theorem. But unfortunately, that will generally not be true. We have to specify the prior and the sampling distribution to do inference and prediction, and we have to specify on top of that the action space and the utility function to do a decision on top of that. And those 4 ingredients, figuring out how to intelligently get from the real world problem that you started with to a good specification of those 4 ingredients is an open-ended problem in the sense that it's sort of like trying to build artificial intelligence engines that are much better than the ones we have now. How to get from how humans actually process thought to being able to get a machine to do that, that's still an open problem. And the same thing is true in statistics. The mapping from the scientific context to those 4 ingredients is where all of the interest lies once you get to use the 4 ingredients, get a little practice with the 4 ingredients. So the top of this page here is the equation that I got to on the previous page, except that I stuck in, on the handwritten pages, except that I stuck in what the sampling distribution actually would be. It would be the product of those theta to the y, 1 minus theta to the 1 minus yi things as I runs from n plus 1 to n. And as I mentioned before, the great thing about De Finetti is that he draws this distinction between parameters being unobservable and data values being observable. And so that's why predictive distributions are so great. We can create predictive distributions for data that have not arrived yet. That's basically what sampling distributions are about. But it's, as a model checking exercise, it's a great thing to be able to construct predictive distributions for future data values based on the data you've seen already. Because that way you have a chance to compare the future data values with your predictions of them, and that's an automatic feedback loop in good model building. You'll discover that you have a bad model if your predictive distribution leads to predictions that don't match well with the reality. And we can even do better than that, because sometimes you don't have to wait for the future data to occur. If you regard the future data as similar to your current data, if you regard it as exchangeable with your current data, then you can set aside with cross-validation, you can set aside some of your present data as a proxy for the future. And that way you have the opportunity to model with part of the data in that cross-validation way I said before, and then build predictive distributions for the data values in the validation part, thinking of it as a proxy for future data. So there is a way forward to discover whether Bayesian models are good or not, and it's all based on prediction and comparing predictive distributions with what actually happened. So our principal diagnostic, and that's going to be quite different from the frequentist way to diagnose models, our principal diagnostic tool in Bayesian modeling is going to be predictive distributions, comparing predictive distributions with the actual data values. So as I say at the bottom of page 31 here, the De Finetti approach to modeling emphasizes the prediction of observables as a valuable adjunct to inference about unobservables, and there's at least 2 good reasons why this is important to bear in mind. The history of statistics, and I haven't told you guys that much about it, but the 20th century was largely a frequentist century. In one reason for that is that the Bayesian calculations were too difficult to do for many decades of the 20th century. But as a result of the fact that the 20th century was largely a frequentist century, it turns out that the only thing of that list of things I said we do as statisticians, namely inference, prediction, and decision, the only thing that the frequentists do reasonably well is inference. And so basically, there were 4 or 5 generations of people trained in statistics in the 20th century to think that the only statistical problems were inferential problems. There isn't a very good narrative in the frequentist story about how to do predictions. And as a result, people got in the habit of looking at scientific problems and pretending that they were inference problems when they were really prediction problems. And this is a bad habit that we need to get out of in the 21st century now that we have good tools for prediction. So there's an example here at the top of this next page. I can ask when I'm comparing 2 drugs, for example, in a clinical trial, or 2 different ways of setting up a web page in an A/B trial here in the Valley. I can ask an inferential question like, is drug A better than drug B on average across many patients for lowering blood pressure? That's an inferential question because it's about a population parameter, namely the average difference between the outcomes for the 2 drugs across all the people in the population you're trying to generalize to. But if you're a doctor and you have a patient in front of you, the ultimate question is not that question. It's instead, how much more will drug A lower this patient's blood pressure than drug B? And that's a predictive question about actual data. And so people in the 20th century tended to ignore that second question because it's predictive and it doesn't look like the inferential questions that they knew how to answer with the frequentist paradigm. It's like that old saying about if all you have is a hammer, then everything looks like a nail. And the whole 20th century, the frequentists, the only hammer they had was an inferential hammer. So as a result, things that were inherently predictive were confused, and it was thought that they were actually inferential questions. And also, as you'll see later in this course, there's a big problem in that there are many situations involving making a decision in which people got in the habit in the last century of using an inferential tool to make a decision, namely that thing called hypothesis testing. And it turns out that the hypothesis testing story, as invented by Neyman and Pearson, is actually in many cases, a very bad way to make decisions. It's not the right way to do decisions. They invented it as an inferential tool, And because the frequentist story didn't have a good narrative about decision in the past century, people started using what they had. They used this hypothesis testing tool, which was meant for inference. They used it to make decisions, and it actually turns out not to be very good at making good decisions. So we'll have to see how that goes as well. Right. I'm not claiming that that first question is irrelevant. In fact, the first question is a health policy question. For example, if you were the National Health Service in England, you would be more interested in the first question than the second one. But if you were a doctor trying to figure out what to do, you're more interested in the second question than the first one. And the point I'm trying to make is that the frequentist approach was essentially to pretend that second question didn't exist at all in the past century, and I think we can do better now. And the other reason that prediction is good to focus on is the thing I just said a minute ago. Good diagnostic checking is predictive in nature. Essentially, you can conclude that you know that an inference about an unobservable parameter can never be directly verified because you never know what the truth is. But often you can reasonably conclude that inferences about the parameters of a model that makes bad predictions, you can conclude that those inferences are probably suspect as well. So we're going to use over and over again in the later stages of the course an approach to deciding whether models are good enough, and whether one model is better than another by asking how well the models make predictions for data values that were not used in their fitting process. And okay, so let's go ahead and talk about the prior. De Finetti's theorem for binary outcomes says informally that if I'm trying to make internally consistent probability judgments about a series of ones and zeros that I judge exchangeable, I may as well behave something like a frequentist in my sampling distribution being IID Bernoulli, but a frequentist with a prior distribution. And now the question, of course, becomes where does the prior come from? And it's an important thing. First, you might have said, well, maybe De Finetti's theorem will tell us what the right prior is, but it's actually an important thing in his theorem that it doesn't tell it. In other words, the theorem is open to all sorts of possibilities for what your information might be external to the data set. It says basically any prior distribution that is a proper prior that actually integrates to one could have been part of someone's coherent probability assessments. And so the theorem doesn't provide any guidance at all, and we're still faced with this question. What should we do for the prior? You probably know by now from having used a lot of software that if there's a piece of code that a lot of people use, and it has an aspect about it that some of the people in the user community really like and other people in the community really don't like, they tend to talk about that thing in quite different language. The people who don't like it call it a bug, and the people who do like it call it a feature. And it's the same thing. It's the same thing in this program. It's just two different names for it according to whether you like it or not. And basically, people who have not thought about probability in an information way tend to regard the need to specify a prior as like a bug, because it seems like it's another thing you have to do in order to get an answer. And why do I have to do that if Fisher says I just have to think about the likelihood function, for example? But in fact, when you're trying to construct summaries that represent the totality of your information, you have to bring in that extra information if you have any external to the data set. And so people who think about the world from an information point of view regard the same need to specify a prior not as a bug at all, but as a feature, because it gives you an opportunity to bring in information external to the data set. And from Bayes' theorem, the prior is supposed to be a summary of what you know and don't know about theta external to your data set. And so where could that knowledge come from? Well, it could come from previous data sets of which you're aware that you judge to be relevant. It can come from relevant literature. It can come from asking expert opinion from people that you believe should know something about this. It could come from lots of different sources. You want those sources to be good, and I put the word good in quotes, and I'm claiming that such information is almost always present and should presumably be used when available, and then the issue is how to make use of such information well. And again, I put the word well in quotes. And so everybody could agree, if I'm allowed to not define the words good and well, that those all seem to be sort of motherhood and apple pie things to say, but now I want to say what I mean by good and well. And one way to think about a prior is to ask yourself, after it's all over and done, and you get to find out what the right answer was predictably, are you proud of your results? And so one way to describe what we're trying to do here is to choose a prior that you'll retrospectively be proud of, in the sense that your predictive distributions for the observables actually look like how the observables landed. So I'm literally thinking about a situation, and we'll see how to do this in the very next case study after this one, a situation where I have my data values, and the very simplest data sets just look like a column vector of real numbers of length n. So think of each of the y's as just a real number. A simple thing I could do to see whether the model's any good is to set aside one of the observations. For instance, I'll set aside y1, and I'll take the data from y2 to yn, and I'll use that to construct a predictive distribution for y1 given all the other data values. And suppose the predictive distribution, we're working with continuous y's, and suppose the predictive distribution looks sort of like this, for instance. Then I can ask myself, so this is the predictive distribution. I can say to myself, well, did it do a good job or not? And that's going to require comparing that distribution with what the value of y1 actually was. So if I find out that y1 actually did land right there, then I can say, well, that looks okay to me because it's not too far from the middle of the distribution. I would like most of my predictive distributions to be centered rather near what the actual data values turn out to be. And moreover, I can keep doing this. I can work out the predictive distribution for y2 given the rest of the data. So let's agree on the notation y subscript minus k, meaning the data vector with observation k omitted. So y1 up to yk minus 1, comma, yk plus 1, comma, up to yn. So I want to think about now the predictive distribution for y2 given y minus 2, and that might look like some other distribution. And then I could see, well, maybe y2 fell way out there. What you're starting to see is that the fact that any one particular observation landed one place or another in a distribution does not automatically either completely validate that distribution or invalidate it. Because after all, rare events happen about as often as they should. And so you can't say that something wrong with the model if a rare event has occurred under the model unless lots of rare events occur under the model. And so we can do something, again, that has almost a frequentist character here. We can create some measure of summary of the distance between an observation and a distribution for that observation, and we can aggregate it across the whole data set. And that can come up, that could turn out to be a good diagnostic, for example. So in doing so, I would like two things to be true. I would like the things that I had over here on this page, namely, I would like my predictive distributions for the observables to be well centered near the actual values and also to have uncertainty bands around them that correspond well to the realized discrepancies between the actual and predicted values. And so I'm thinking about calibration again, as I've talked about before, and this is a kind of calibration that pays attention to two things. Am I calibrated more or less correctly on average? And also, do my give or takes, my uncertainty bands, are they about the right width? And those are the two main things you would think about as first and second order things you'd look at to see whether you're decently calibrated. Now, it's a basic fact that there's no guaranteed way to do this, to arrive at that state of affairs in that box here on this page, just as there's no guaranteed way to arrive at a good frequentist model. In fact, frequentists are in the habit of, or in the last century, they were in the habit of taunting Bayesians by saying, well, where did your prior come from? And if you wanted to stoop to that level and bicker with someone, the thing to do as a Bayesian is to ask right back to that person, well, where did your likelihood come from? And whenever the data have an observational character, the person will have to say, well, I didn't know what the likelihood was, and I hunted around in the data to find something that looked okay. And we can both agree right then that there's an ad hoc component to what they're doing. And so, as I said in week one, everything that we do in statistics involves judgment and assumptions, and it cannot be avoided. So you can't condemn the Bayesian paradigm by complaining that there's no guaranteed way to arrive at this kind of calibration, because that same complaint applies directly to the frequentist paradigm as well. Now here's a couple general comments about how to end up with a good prior. Firstly, to develop a prior based on expert opinion has an actual verb in English. It's called to elicit a prior, and there's a long literature on it, and it brings together ideas from statistics on the one hand and a branch of psychology that has to do with human perception on the other hand. For instance, if you want to use a normal distribution for a prior, and you're trying to work out the mean and standard deviation, it turns out that human beings, are not very good at thinking about standard deviations. And no surprise, we've only had it as a mental construct as a species for about 100 years, and yet we've been thinking at least informally, quantitatively, for tens of thousands of years now, so it's a really new idea, and people aren't very good at assessing standard deviations. What's your guess? Would people, when they're asked to assess standard deviations, they come up with numbers that tend to be too high or too low? What would your guess be? Mostly people end up getting standard deviations that are too small. We, as a species, have a bias toward optimism. I think it's part of what helped us be successful in getting down out of the trees as monkeys, basically. If you really did a full assessment of everything that could go bad today, you wouldn't have even got out of bed this morning, right? What that translates into a bias in which we tend to underestimate how much uncertainty we have about things, and that translates into standard deviations that are too small. In fact, they've done studies and shown that professional statisticians are not that much better than lay people at estimating standard deviations when you ask them questions on the standard deviation scale. But what perceptual psychologists have found is that people are much better at thinking about percentiles and quantiles than they are at thinking about first and second and third moments of a distribution. So if you wanted to elicit a normal distribution, you can do so by asking questions like, where is the place along the number line that you think the thing we're thinking about would tend to fall half of the time to the left of that and half to the right? And that's a median, and that's the same as the mean in the normal curve. And then to get the standard deviation, you can ask them the same question except for 25% and 75%, and you can translate directly from the interquartile range to the standard deviation in the normal model. So that turns out to be a much better way to get information from experts than to just ask the question directly. And there's a whole literature on this that you could read if you're interested. When I worked at the RAND Corporation many years ago, we spent a lot of time convening expert panels to try to bring together consensus about what was the best way to do medical care and so on. And a tremendous amount of thought went into the process of figuring out how to ask the experts questions so that their answers came at you in a relatively unbiased way. Because a basic thing we know about humans is that the way you ask a question can often influence the answer you get. And that turns out to be true even with experts and them experts trying to talk about their areas of judgment. If you take the log of Bayes' theorem, this is now equation 28 on page 35. If you take the log of Bayes' theorem and ignore the normalizing constant, it says log posterior equals log prior plus log likelihood. And that turns out to be a scale in which to think about information. So information is additive on the log scale. And so basically the posterior information equals the prior information plus the data information. And that can help you in deciding how strong you want the prior information to be. In effect, a good thing to do, as I was showing you on that sketch a little while ago, is to plot the prior and the likelihood and the posterior densities all on the same picture, or at least plot them next to each other. Here, having shown you this progression from prior to likelihood to posterior, I could have made a picture in which all three of them landed on the same scale, and that would be a very good thing to do. And in fact, in this case study, we'll look at it after lunch. I'll do that. And what you can do is you can see graphically whether the prior seems to be having more of an influence on the posterior informally than you wanted it to. So, like it says here on page 35, close attention can be paid to the information content of the prior in this means by, for instance, density normalizing the likelihood and plotting it on the same scale as the prior and the likelihood. And it's possible for a small amount of data, because total information, posterior total information, equals prior information plus sampling, plus state information. With a small sample size, it's possible for the prior to swamp the data. And you don't want that to happen unless you really, really do have strong prior information to serve as the basis of your overall posterior inference. There are some situations in which that arises. And in fact, I know that some of us in the Valley are trying to use information from multiple sources to bring in informative priors, to construct informative priors that sharpen our inferences, for example. But we don't want the prior to swamp the data unless there's a very good reason for doing so. And you can also take comfort from the flip side of that same coin. With a lot of data, what will happen is that the data swamps the prior, and then it doesn't matter very much what you write down for the prior, because all roads are going to lead to Rome pretty much. And there'll be an example of that in this case study after lunch. Third thing to say in general When I notice that I'm quite uncertain about how to specify the prior, then I obviously should use sensitivity analysis. What I can do even before the data have arrived is a form of what people call pre-posterior analysis. I want to explore the mapping from prior to posterior distribution, and I can do that before the data have arrived by simulating data sets that I think are like what I'm going to see when I actually get the data, and then simply try writing down a bunch of priors and updating them with Bayes theorem to posteriors and looking at the nature of the updating and seeing if it looks reasonable or not. So that's a simple thing you can do, and people do it all the time. And then the other thing to say, that I've already said, is that calibration, which I've said is a criterion that can be helpful in deciding whether you have a good prior or not, can be judged by that form of cross-validation that I mentioned to you before. So here we go. I would like to quantify the following information base. I personally know from the literature, the medical literature, that the 30-day heart attack mortality rate given average care and average sickness at admission in the U.S. is about 15%. And that should give us all a little bit of thought as a matter of whether you want to have a heart attack or not. Averaging over how young or old you are and how sick you are with other things and so on, about 1 in 7 people die of a heart attack within 30 days of getting admitted to the hospital for it. So let's not have a heart attack. By the way, you may have a feeling that, I don't know, you probably heard a lot of things about how the American healthcare system isn't that good. And certainly there are things that we can complain about, but there are lots of, we do moderately well on the international stage, particularly when you think of the comparisons in the following way. The American healthcare system, the overall aggregate numbers are a kind of weighted average of among the very best care in the world for the people who can get it and people who get almost no care at all. So we basically have a little third world country hidden inside America of people who can't get any health care. It's better under Obamacare, but there's still going to be 10 or 20 million people in the country who still won't have access, maybe even more, who still won't have access to decent medical care. But suppose I gave you the following and asked you your opinion. We go around and measure quality of care at hospitals. I did this with other people at the RAND Corporation. And I identify the hospitals that are the best and the worst. And I ask you to compare the heart attack mortality rates in America between those two extremes. So what would you guess is the multiplicative factor? The 30-day mortality rate at the best hospitals is lower than the 30-day mortality rate at the worst hospitals in America by a multiplicative factor of about, if the country was any good, you'd want that multiplier to be 1, right? You'd want to have uniform good health care everywhere, but it's going to be bigger than 1. How much bigger? I'm averaging over sickness of what prior? But we're measuring quality in a way that adjusts for how sick the patients were. So don't worry about that either. We'll trust me that I can come up with something like an adjusted outcome based upon how sick people were and so on. Yeah, the answer is 4 to 5 times. The chance of getting a heart attack is 4 to 5 times higher in the worst hospitals in America than in the best ones. If you have to have a heart attack, try to arrange to have it on the sidewalk out in front of a major teaching hospital in a big city. That's your best chance of surviving the heart attack because the quality of care is the highest in those hospitals. Try not to have it while camping in West Virginia or someplace like that. Whatever rural hospital they bring you to, unfortunately, the rural hospitals in this country tend to be years behind the major teaching hospitals in dissemination of best practice. So it's worse than you think. It's a good question. The outcome standard is worse in a lot of other countries, but I don't know how big that gap, how that comparison goes. That's a good question. I'm going to look into that a little bit. I don't know the answer to that. So, I know that the background rate for averaging across sickness and process is 15% roughly. Personally, I know rather little about care or patient sickness at this hospital for the reason I said. I've been living in the area for more than a decade, and there haven't been these major stories about Dominican treating vastly sicker or less sick patients, Dominican having vastly better or worse outcomes. So that means that I would therefore be somewhat surprised if this theta thing, the underlying heart attack rate, was very small or very big. And I'm going to choose to quantify that by saying I'd be surprised, at least somewhat surprised, if the underlying rate was much less than 5%, which is 3 times better than the national average, or much more than 30%, which is 2 times worse. And you can see that that statement C is a bit wobbly. I've just tried to pick out some numbers that represent the idea of being surprised if things were that good or that bad. And so you'd want to do sensitivity analysis on that number 5% and on that number 30%. And also I have to quantify for you the idea of being somewhat surprised if the actual number fell outside that range. And in fact, in what I'm about to show you now, I'm going to quantify that by putting 95% prior mass inside that range. And again, 95 is a number that I would need to do sensitivity analysis on. And what you'll find when you do that with this data set is that because we have 400 observations, reasonable sensitivity analysis deviations from all the numbers I just mentioned to you lead to essentially the same posterior distribution. The prior is relatively insensitive to how you specify those details. So I'll cut ahead on that and just tell you what the answer is. Sensitivity analyses mean that these things don't have to be pinned down that precisely with 400 observations. With 40 observations, it would be another matter. Now, I want to center this distribution somehow around 15%, and I could center it at the mean or the median of the mode. I'm going to center it at the mean, and again, you could try the median instead and so on. None of that stuff matters. So I would like a flexible family of probability densities on the unit interval, one of whose members has a mean of 15%, or 0.15 in decimal terms, and a 95% central interval that runs from 5% to 30% mortality. And if you are accustomed to the frequentist story, you may not have had much use for this distribution before, but for the Bayesian story, there is such a flexible class of distributions. It's called the beta family, and it's indexed by 2 numbers, alpha and beta, and we're about to use it as a prior distribution for a parameter. And so people call the alpha and the beta in this prior distribution hyperparameters because they are parameters of the prior distribution for the parameter. So if you want to use the strict language for it, the alpha and the beta are so-called hyperparameters. And my trick is going to be I'm going to pick the alpha and the beta to generate a member of the beta family that does have a mean of 0.15 and 95% central mass between 0.05 and 0.30. That's going to be my plan. Yes. Yes. Yes, he's saying that you should, I'm doing this for the sake of the video, and I should have done that for all previous questions too. I apologize to posterity for not having done a good job of that. He's saying, shouldn't you take account of the fact that major teaching hospitals, there's a kind of a feedback effect. Major teaching hospitals tend to be in places where people have a greater awareness about health issues, and that therefore someone who was on the edge of having something bad happen to them is more likely to get themselves to the hospital faster than someone who might live in a rural area. That's true, and there have been some attempts to account for that, and when you do, you still get nasty disparities like the one that I was mentioning. So this family turns out to have an ugly-looking density form. The important part of it is theta to a power times 1 minus theta to another power. That will get you a density on 0, 1, it turns out. And to make it a proper density, you have some restrictions. Alpha and beta have to be restricted to be large enough to get a proper density. And so they have chosen to make the restriction that alpha and beta are positive. And with that restriction, you have to write the density in the form theta to the alpha minus 1 times 1 minus theta is a beta minus 1. We could have absorbed the minus or plus 1 in the restriction instead and just had theta to the alpha, 1 minus theta to the beta, but that turns out not to be as convenient as this story here. And so it turns out that the normalizing constant for this family is a ratio of some products of some gamma functions. And gamma functions, you may recall, are what happens when you try to evaluate a particular integral that has no antiderivative. And that integral comes up so often in math that rather than just doing something else, they just give it a name. They give the integral a name and work with it from there. And so R, for example, and Maple and MATLAB and all these standard packages have a function to calculate gamma. You may recall that gamma is a kind of, the gamma function is a sort of continuous generalization of the factorial function, because gamma of an integer n equals n minus 1 factorial. And that should tell you also that you're in trouble in working with this function when the thing you put into it is a big number, right? Because we know that 500 factorial is a really big number. And so the natural thing to do instead of working with the gamma function then is to work with the logarithm of the gamma function. And that's going to be much more numerically stable. So for example, if you were writing your own code to evaluate this density, you shouldn't ever write it on the density scale. You should write the code on the log density scale and then exponentiate the resulting number at the end of your calculations. That will make sure you don't have underflow or overflow problems. So that happens a lot in Bayesian calculations. Everything in Bayes theorem is based on taking products, right? And when you start taking products of things that are really big or really small, you can have underflow or overflow problems. So we often go to the log scale as fast as we can. This family turns out to have a wide variety of distributional shapes hidden inside it for different values of alpha and beta. You'll notice one popular choice is if you put alpha and beta both equal to 1, then the theta part disappears and you just get the constant, in other words, the uniform distribution. So that's the 1, 1 uniform distribution there. And also, if you make both the alpha and beta smaller than 1, for instance, a half, you can get these bathtub sort of distributions where this actually, strictly speaking, goes off to plus infinity at 0 and at 1. But you'll notice that the 0.5, 0.5 distribution and the 1, 1 distribution have the property that they're both not too far from being flat across a broad range of theta values. In fact, of course, the uniform achieves that exactly, but the 0.5, 0.5 beta does so at least approximately. And in fact, in that picture I showed you a minute ago, I should have mentioned something relevant to that, so let's take a look. We got, with a completely flat prior, uniform prior, we got that the posterior and the likelihood coincided. But what if I made a prior that tended to be close to flat in the region where the likelihood was big, and then you can see what would happen if, as long as I made sure that was true, I can do practically anything I want with that prior anywhere else. Because by the time you get out in the likelihood to a place like 0.7, the likelihood is on the order of 10 to the minus 1,000. And so basically, you can put any crazy thing you want outside the region where the likelihood is appreciable, and it doesn't matter, because the product will still be close to 0. So that's a principle called stable estimation that was first noticed by these people called Edwards, Linneman, and Savage, Jimmy Savage being a prominent American Bayesian in the 1950s and 60s. And basically it says, if you want to ensure that the prior distribution doesn't have a lot of information in it, then just try to make sure that it's relatively close to flat in the region where the likelihood is big. And then don't worry about the details outside. So in that regard, for instance, as long as you were working with a data set where the likelihood function was sharply away from 0 or sharply away from 1, this unpleasant asymptotic behavior of the 0.5, 0.5 density won't matter, because as long as the likelihood function is concentrated around, in our case, it's going to be concentrated around 0.18, and that's going to turn out to mean that the bathtub part has no effect on things at all. If you use small values but not equal to each other, you get asymmetries. So the 2, 3 distribution has a long right-hand tail constrained to be in the unit interval. You can create beta distributions that look a lot like log normal densities, except constrained to be from 0 and 1. And what starts to happen as the alpha and the beta get bigger is that there's a central limit tendency. See how when I use 30, 20, I get something that looks rather more like a normal curve than this skewed thing down here. There's still a little bit of a long left-hand tail to it, but actually as alpha and beta get bigger and bigger, you get beta distributions that look more and more like the normal curve. That's a kind of, it's an example of a kind of a Bayesian version of the central limit theorem, as it turns out. So that's a good thing. It has a wide variety of distributional shapes. And the other reason that is interesting, it's interesting in problems like this, is the following. Did I talk last time about the idea called sufficiency? Did we talk about that at all? That the sum is a sufficient statistic in this problem? Okay, so the next thing to notice, carrying on from sufficiency in this problem, is that The likelihood function in this problem, as we saw, looks like theta to the s times 1 minus theta to the n minus s. And we know that Bayes' theorem says that the posterior is going to be a normalizing constant times the prior times the likelihood. So let's stick in the likelihood. It's going to be a normalizing constant times the prior times theta to the s, 1 minus theta to the n minus s. Now, one thing that would make calculations easy, and I'm not saying this is always the right thing to do on scientific grounds, but one thing that would certainly make calculations easy is if you could pick a prior so that the product of the prior and the likelihood function had the same mathematical form as the prior. Because if you could do that, then once you understood what that mathematical form was in the prior, you don't have to do any new math for the posterior. It's the same distribution, maybe with different parameters in it. So one idea to simplify calculations is to try to find a prior that has the property that the product of that prior times the likelihood function has the same mathematical form as the prior did to begin with. And in this case here, you can see that one way to do that is actually something related to that. If we make the prior have the same mathematical form as the likelihood function, then it turns out for this particular likelihood function, two functions that are the form theta to a positive power times 1 minus theta to another positive power, two such functions multiplied together give you another function of the same form. And so a kind of computational trick that makes the problem easy would be to choose a prior that has the same mathematical form as the likelihood does, namely theta to a power times 1 minus theta to a 1 minus power, to a 1 minus theta to another positive power. And that's exactly what the beta distribution does. Because remember what it says, the beta distribution looks like theta to the alpha minus 1, 1 minus theta to the beta minus 1 times some other normalizing constant, and all those constants are going to get absorbed into each other. And look, the product of two such things is another such thing. And so when we're done, this is over here is going to be theta to some power times 1 minus theta to some power. In other words, the prior is going to be beta, and the likelihood function is going to be beta, and the posterior distribution is also going to be beta. So basically, it's a sort of all in the family thing. Having chosen a problem that involved this particular likelihood function, we can ask ourselves, is it true that the product of two such functions is another such function? And that turns out to happen sometimes in Bayesian calculations. And if that's true, then by choosing a prior that has the same mathematical form as the likelihood function, the product, which is normalized to be the posterior, will have the same form again. And all three of them will be from the same family, and then you only have to learn about that family, and then you understand how to make calculations. So, pretty good idea. It was first noticed by Mr. Bayes all the way back in the 1750s. It wasn't given a name, actually, until the 1950s, and by these guys at Harvard called Rafa and Schlafer, and they called such a prior conjugate to the likelihood that you're interested in. So, like it says here on page 39, the Reverend Bayes himself noticed back in the 1740s that a prior of that form, theta to a power, 1 minus theta to another power, produces a product which is of the same form. Wait, oops. Let's try that. The same form as the both the prior and the likelihood, and so the computations are now more straightforward. And so now we're going to agree that the beta family, the language, the jargon is conjugate to the Bernoulli likelihood, and it turns out also to be conjugate to the binomial likelihood, because the binomial is just what you get by summing up a bunch of Bernoullis. And so it's a little bit hard to specify out mathematically what the idea is, but just basically you try to find a family of prior distributions so that the product of members of this family with the likelihood function will also be in the family. And as soon as Mr. Bayes had noticed this idea, it was a great thing for him to notice in the 1740s because he wouldn't have had a prayer of making any of the calculations he needed to without conjugacy. So conjugacy didn't have that name in the early days, but it was invented because Mr. Bayes was trying to calculate an answer, and if he'd used practically any other prior, he would have been in some trouble. So right at the beginning, conjugacy started out as an idea that was not necessarily driven by the science of the problem. Instead, it was driven by expediency. It was driven by making sure that the calculations were easy to do. People today with Markov chain Monte Carlo are no longer restricted to conjugate forms. You can get good Bayesian answers with practically any prior you want. But there are some advantages of creating models in which there's a kind of conditional conjugacy, and I'll show you why that's true when we get later to the stuff later on. She says that sometimes you don't necessarily have a closed form for the likelihood function. And there are problems in which the likelihood function is like a black box and can only be evaluated numerically. In other words, you input a parameter vector and you have to solve a system of partial differential equations, for example, to get out the value of the likelihood function at that particular parameter vector input. In problems like that, conjugacy is right off the table. There's no way to create anything that does the right thing. So this is restricted to a small set of models, quite a rich set it turns out, but still a rather small set of models in which the likelihood function has the special property that any two such functions multiplied together gives you back another function of the same form. Does that work for normal curves, by the way? Is the product of two normal curves another normal curve? Yes. Does it work for, well, we'll talk about the other ones later on. It turns out there's a bunch of families, a bunch of sampling distributions for which it does work. Okay, so now that turns out, conjugate analysis turns out to be one of only two rather general ways of getting closed form answers in the Bayesian story. The other one is a kind of asymptotic analysis in which everything becomes normal curves in the posterior, and that's not that useful because we often don't have enough data for that to be true. So let's now see how I would solve to work out the alpha and the beta that solve my problem. So I want an alpha and a beta such that the mean comes out 0.15 and the 95% central interval comes out between 0.05 and 0.30. So you can do some calculations, and you'll find that when you look on the handout I've given you about basic distributions from the Gelman book, the mean and the variance of the beta distribution are given to us, and the mean turns out to be alpha over alpha plus beta, and the variance turns out to have what looks like an ugly expression, but is actually quite interpretable, as we'll see a bit later. So I can drop the problem down from two equations and two unknowns to one equation and one unknown by setting alpha over alpha plus beta equal to 0.15 and solving for beta. And so beta comes out 17 over 3 times alpha. And then I have a little integral equation I have to solve, namely 95% of the prior mass has to be equal to what you get by integrating the beta distribution with parameters alpha and 17 over 3 times alpha from 0.05 to 0.30. That's supposed to be 0.95. So that's a little equation in alpha, and you can solve it for alpha. And then, of course, plug back in to see what the beta is. Can that equation be solved in symbolic form? Probably not, right? Because it would involve having the beta distribution have an antiderivative, and the whole point of that gamma normalizing constant is it doesn't have an antiderivative. That's why those gamma functions came in. So you cannot solve for this in symbolic form, but you can solve for it readily in numerical form. And you could do this either in R or in Maple. When you do that, what you get here is that alpha turns out to be 4.5, and beta turns out to be 25.5. And so I've now plotted on page 41 the beta distribution with those two particular parameters. And I want to look at it for a while before I actually use it and see if it's captured the information the way I want. It's asymmetric, which is what I wanted it to be, because I had an asymmetric requirement that, in fact, what I did was I put 2.5% of the mass in the left tail and 2.5% in the right tail, but one of them was 3 times better, the other one was 2 times worse. That creates a long right-hand tail behavior, which is just what I want. It's centered in the mean sense at 15% mortality, which is reasonable. And the prior standard deviation, when you plug the numbers into that formula a minute ago, you take the variance formula, square root it, turns out to be about 0.064. So it's as though the prior says that I think the underlying mortality rate at this hospital is around 15%, give or take about 6 or 7%, and that's just what my prior describes. I would be very surprised if the actual rate were up around 35 or 40% or higher, and I would be very surprised if it were down around 1%. That's what the prior is basically saying. Okay. What's that? That's right. So this is a first stab, And then I can go back and change the 0.95 and the 0.05 and the 0.30 and other things to see how much this changes. And the answer is it doesn't change very much at all. So as I mentioned, in the usual jargon, alpha and beta are called hyperparameters because they're parameters of the prior distribution, which is itself a distribution for a parameter. But we don't have to dwell on that too much. So now we have a hierarchical representation of the model that looks like equation 33. It says, well, first of all, if you knew what theta was at the bottom level, your model is that the y's are conditionally IID Bernoulli theta. And that is the sampling distribution or likelihood part of the model. Then at the next layer, we say, if you knew what alpha and beta were, theta would be like a draw from a beta distribution. That's our prior information. And then at the top level, I deterministically set alpha equal to 4.5 and beta equal to 25.5. And so you can see, having written it in this way, that's another way to perform sensitivity analysis. I could, instead of going back and varying the 0.95 and the 0.05 and the 0.30, I could now put another layer in this distribution, in this story, in which I varied the alpha around 4.5 and I varied the beta around 25.5. That would be another way to explore the sensitivity of the posterior to small changes in the prior specification. And as soon as you have that idea, of course, we humans tend to operate on a theorem more often than we should of the form, if more is better, then even more is even better, right? So as soon as you have this idea, you say, well, why not go ahead and put a prior not only on alpha and beta, but then put a prior on whatever that was above that and keep going. And eventually you'd have a kind of hierarchical model with an infinite regress, right? Because there could be as many layers as you want. The grand thing about that is that you can try it if you want, but you'll find that after a certain point, it has no effect at all on the posterior. Basically, there's a kind of informal theorem you can show, which says that the farther the layer hierarchically is away from the data layer in the model, the less that layer matters in the posterior distribution. So basically, there's no point in going much farther with this hierarchy than just stopping right here and maybe fiddling with the 4.5 and the 25.5. And as a practical matter, of course, everybody always stops these analyses when they run out of time and money also, so that's another way to, in practice, limit the number of levels of the hierarchy. I rarely see practical hierarchical models that have more than 3 or 4 levels in them. There's hardly ever any need to go any deeper than that. All right, well, what does Bayes' theorem say here? Well, there's the prior, there's the likelihood. You multiply them together, and out comes the expression on the last line of equation 34. So the posterior is another member of the beta family. And look how simple the updating rule is. The prior was a beta with parameters alpha and beta. And what happens in the posterior is that alpha updates to alpha plus s, where s is the number of people who died. And beta updates to beta plus n minus s, where n minus s is the number of people who lived. So in this model with the conjugate story, that's a very simple way to describe what happens. And it also leads as a suggestion to a really important insight about how prior distributions can be regarded literally as information sources as being equivalent to data sets. So let me take a minute to tell that story. And that'll probably get us pretty close to lunch, as it turns out. So here's my data set, y1 through yn. There are n observations here. And you remember that they are 1s and 0s. And so if I wanted to, I could sort all the 1s into a block and all the 0s into a block. And in fact, having done that, because they're 1s and 0s, the mean of this data set is S over n, as we saw when you work with 1s and 0s. And that means that it's as though, in fact, it literally is, we have S 1s and n minus S 0s in this data set. And the mean comes out S over S plus n minus S, and that comes out to be S over n. So that's the data level in this diagram I'm drawing here right now. Now, try something on for size with me for a minute. Just try it. Suppose the prior distribution, being this beta, alpha comma beta distribution, suppose you tried to think of that as like a data set. Well, since the data itself is 1s and 0s, it would be most natural to think of the prior data set as like 1s and 0s as well. And the prior mean comes out alpha over alpha plus beta. So look what just happened. The data mean was S over N, which can be written S over S plus N minus S, and alpha over alpha plus beta. So there's a formal analogy between alpha and S on the one hand, so it's as though the prior has alpha 1s in it, and beta acts like N minus S, so it's as though the prior has beta 0s in it. And indeed, if you had a data set with alpha 1s and beta 0s, the mean would be alpha over alpha plus beta. And now here's the precise sense in which the prior can be thought of as equivalent to a data set. Imagine the following two analyses. Analysis 1, beta, alpha beta, prior, Bernoulli likelihood. Bayesian, get the Bayesian posterior distribution and base your answers on that. So that's a straightforward way to analyze this data just using what I showed you. But now think about analysis 2, and here's how analysis 2 might go. If you were a non-Bayesian and you like to use likelihood methods, and you convince yourself that the prior acted like a data set, then what you would try to do is merge the prior data set with the sample data set, and then do maximum likelihood methods on the merged data set. That's analysis method 2, and it's a remarkable and interesting fact that you get the same answers when you do that. So merge prior and sample data and do a likelihood analysis on the merged sample. And the payoff is that analysis 1 equals analysis 2. So pretty cool. It's as if the prior acted like a data set, and not just any data set, in the same way that the data sample size was n, which was arrived at by adding the s and the n minus s. The prior sample size in this problem, which we could call n0 if we wanted to, is simply equal to alpha plus beta. That's the analogy. You take the s plus the n minus s, you get that much data. Alpha plus beta is how many observations there are in the prior data set. So it's as if the data set gets n votes in the process of combining those two information sources. It's directly as if the data set gets n votes and the prior gets alpha plus beta votes. And in fact, that's how Bayes' theorem works. It's always a compromise or weighted average between the prior information and the data information. And what we're seeing here is that with my particular prior that I've used, alpha was 4.5, if you recall, and beta was 25.5, and the sum of those two numbers is 30. Here, 4.5, here, 25.5. And so the prior sample size here, n0 equals 30, and the data sample size in our problem was 400. And so basically what's going to happen in Bayes' theorem is that the posterior distribution acts like a data set with 430 observations in it, binary observations in it. And that means that in the weighted average or compromise between the data information and the prior information, the prior is going to get 30 votes, and the data set's going to get 400 votes. And so qualitatively, what do you expect the posterior to look like? Will it look more like the prior or more like the likelihood? More like the likelihood, in fact, a lot more like the likelihood than the prior, because the data set gets 400 votes and the prior only gets 30 votes. 400 over 30 is a ratio of about, what is that, 12 or 13? 400 over 30, 3 into 40, 13. And so basically, the ratio of prior and data sample sizes is about 13 to 1. So in the weighted average process, the data set gets 13 times more weight than the prior does. That means the likelihood is going to look a lot like the posterior. Quite a bit, but not identical. So that all of this assumes the conjugate prior. That's right. If you don't have a conjugate prior, then in fact, what I wanted to say about that is that it turns out that whenever you can find a conjugate prior, this story about the prior being equivalent to a data set and being able to work out what the prior sample size is, that story always works. So that's another advantage of conjugacy when it makes sense to you scientifically. If you can get a member of a conjugate family that actually matches your information, then you have this lovely heuristic in which the prior directly is like a data set, and you can even visualize what that data set is like and work out how much prior information is going in terms of the prior sample size. Moreover, since the likelihood analysis is equivalent to merging these two data sets, the posterior mean has to be a weighted average of the prior mean and the data mean, with weights given by the prior sample size and the data sample size. That just has to follow from this argument here. So that's yet another nice thing that happens with conjugacy. Yes, so when conjugate priors are not rich enough to quantify the information you have, for example, the beta family is lovely as far as it goes, but there are no bimodal or multimodal beta distributions, then the natural thing to think of doing would be to build a prior out of mixtures of conjugate priors. And in fact, there's a theorem due to Percy Diaconis and Don Ilvasacker that says that as long as the sampling distribution is from what's called the exponential family, which is a place where almost all of the standard sampling distributions live, then any prior distribution can be expressed as a mixture of conjugate priors. And you may have to have a lot of mixture components to get whatever the shape is, but any prior can be thought of as like a mixture of conjugate priors. So that's a sense in which conjugate priors serve as the building blocks for creating an arbitrary prior in that mixing kind of way I showed you about mixtures earlier today. Okay, so we have reached lunchtime.